Here we are. Thank you very much all for joining. And I would like to give the word to Rostislav Hriniv, who is the director of the Lviv unit, to say a few words about the new unit and also introduce the first speaker. Rostislav, please.
Hello, everyone. I'm very happy to starting this workshop. As I've already said, ELLIS Associate Unit Lviv is based at the Machine Learning Laboratory of the Faculty of Applied Sciences of the Ukrainian Catholic University in Lviv, Ukraine. So this is the first associate unit, ELLIS Associate Unit. We are a young faculty with strong aspirations to high quality research and education. And our computer science bachelor and master programs are actually top rank in Ukraine. So the research fields of the ELLIS Associate Unit include machine learning with application to 3D computer vision, embodied AI, and these are actually the topics for the first ELLIS workshop, and as well as natural language processing with emphasis on low resource languages, biology and medical imaging, and so on. So this workshop aims to share new results and prospective research directions in machine learning and artificial intelligence in general, and foster collaboration across the ELLIS network and also worldwide, as we'll have speakers outside the Europe even today. So I'm happy to introduce the very first speaker of today's workshop. So please welcome Tetiana Martyniuk. Tetiana got her Master in Science in Data Science at UCU, Ukrainian Catholic University, in 2019. And since then, she has been teaching computer vision at this university. Currently, Tetiana is a PhD student at Andrea Vedaldi in Paris, jointly with the AstraVision group. Her research interests center around computer vision, 3D, deep learning, and generative modeling. And a few featured publications include ICCV papers and ECCV papers and CVPR as well in 2022 to 2019. And I guess that today's presentation has evolved from the project presented on CVPR 2022. So Tetiana, the floor is yours. Please go.
Thank you very much. Thanks for having me. Thank you, Rostislav, for introduction. Yeah, so let me share my screen. And please let me know if you can see it well. I hope so.
Yes, it is visible. Thank you.
Okay, lovely. So yeah, let's kick off. As Rostislav mentioned, indeed, I'm currently a PhD student at AstraVision in Paris. I'm currently working on conditioned 3D scene generation, so it's a little bit different to what I'll be presenting today. But yeah, today I'll be talking about one of our prior works that is called DAD 3D heads. And indeed, it was accepted to CVPR 2022. It's my first author paper, and unfortunately, I didn't get to present it on site. So for me, it's very thrilling today to give this talk, because it's almost like the poster session that never happened to me, really. Yeah, so that DAD 3D heads stands for large-scale, dense, accurate, and diverse. That's where the abbreviation stems from, Dataset, for 3D head alignment from a single image. And it was a joint work between different institutions and, well, UCU on one side, and also Pinata Farms. There was a company that a few of the first authors of the paper were working at that point. So let me start with the motivation where this project even emerged from. Okay, so I'll start with voicing probably very obvious, but still the main challenge for this type of projects. Inferring 3D shape from a single perspective, it's extremely challenging for computer vision. And well, basically, if it's single image, it's sort of a ill-posed problem, right? Now, when we talk about the head shape and, well, identity of a person, the head shape of the same person, it has to be robust to variations in lighting conditions, head pose, various expressions, compound emotions, and other things like, I don't know, facial hair, makeup, occlusions, accessories, etc., etc. And large training sets in the wild images, they of course lack ground truth 3D shape by construction. And well, let me start with introducing the task that we were aiming at. So as you search for 3D head alignment methods and or benchmarks, if you Google that, if you go to Papers with Code, for example, you'd probably end up settling with 3D face alignment. Not many research groups seemed to care at that point too much for the whole skull, while for us it was crucial. Let me remind you what face alignment stands for. So in small font there, it's a task of identifying the geometric structure of faces in digital images and attempting to obtain a canonical alignment of the face based on translation, scale, and rotation. So basically we have an image and we want to fit as good as possible the 3D model onto the image, right? So as I mentioned, it was a collaboration between the company and the research lab. So we were really aiming at the real world task. And in our real world scenarios, the images of people, they're often low quality. They have many artifacts. They're heavily non-frontal. For example, we had a lot of side poses and high pitch poses. They contained occlusions, etc., etc. And we faced following limitations. Like, first of all, at that point, the most popular subset of landmarks that off-the-shelf methods we're working with was the multi-pi subset of 68 landmarks. We needed something more flexible. Also, most of the methods, they relied on 2D landmarks fitting on 2D supervision, and they seemed to fail on side poses in the wild inputs. Invisible landmarks were really off, and I'll show you some examples further. And if we would only resort to simple 2D key points as opposed to 3D fitting, it would allow only for simple animations. This is one of the things that like here in the image, we show what we were trying to do in the company. We wanted to be able to place accessories, to do different like face morphing, 3D effects, also to generate new poses and emotions, for example, to be able to do face reenactment, etc., etc. So we wanted to build up like this whole like plethora of tasks, and for that we needed a really robust 3D model. So we figured that Dataset, the data overall was the bottleneck for us for achieving robust head alignment in the wild. And well, the difficulty comes from lack of pairs of 2D image and 3D model if we are talking about unconstrained environment, right? And as a result, we have ambiguity of the task and reliance on the 3D shape priors. And many methods have been developed to fill the gap of missing 3D annotations. At that point, primarily using 2D landmarks datasets for fitting. As I mentioned, they are really sensitive to the invisible landmarks. You can see in the bottom image all the side poses. This is from the AFLW dataset. When you have invisible landmarks, they would be really off. Other approaches, they rely on pseudo ground truth workarounds like warping, for example. And in the top images, you can see that the warping results don't always look realistic when you go to extreme poses. Other types of datasets, they do rely on 3D scanners to provide an accurate 3D head model that the manual annotation cannot guarantee. However, they operate under controlled capture, right? So instead of being in the wild, they are in the lab. They are often fairly small with respect to the number of diverse subjects. And on top of that, they do not have precise correspondences when it comes to compound facial expressions, because the scans are usually neutral, while we are talking about single image input that could be with various facial expressions. And well, last but not least, most of those methods, they were still doing face alignment, as I mentioned, and we really needed a solution for heads. So in contrast, in our work, we tried to show that without expensive devices like scanners that are difficult to deploy in the wild, we can still collect accurate annotations of 3D landmarks directly from images, and it proved to be effective to push state-of-the-art results for 3D head recovery from images. So that's it for the motivation. Let me jump to the main contributions of the paper. So they are threefold. First of all, we introduced a new DAD 3D heads dataset that has almost 45,000 head images and the corresponding 3D head meshes, and more than 3,500 accurate landmarks per head. And we will talk a little bit later what we mean by accurate, because it's still like pseudo ground truth in a way. Then next, we trained end-to-end model, DAD 3D net, that would predict 3D morphable model parameters from a single head image. And last but not least, we introduced a novel benchmark with the evaluation protocol to quantify the 3D dense heads fitting. Well, let's start with the data set. So here I'll talk about the acquisition. The video is played now. Okay, great. So to create a large-scale data set of in the wild images, we used a proprietary semi-automatic 3D annotation tool. And here you can see how the annotation was happening and how our annotation scheme tried to address the problems that exhibited by existing labeling tools, such as guessing the positions of the correct landmarks for invisible parts of the head. So the annotation process was iterative. The trained annotator person, they would pin the 3D head model to the head image, and then the 3D parameters are optimized under the hood so that the pin reprojection error is minimal. Don't be mistaken, the annotators do not explicitly control or label neither the 3D parameters nor they have access to blend shapes, and they do not really disambiguate between identity and expression. You literally see now like the full annotation process, and that's the only thing that they could do. They could also inspect if in the 3D view, the head shape, like the skull, is not distorted, and if the texture mapped onto the skull looks well, that was it. But that was more like visual inspection. And then if we go to the abbreviation itself, DAD, what does it stand for? So as I mentioned, diverse was the first D. We try to maintain the data set to be like really well balanced over a wide range of poses, face expressions, occlusions. We provide annotations that include age categories, gender, illumination, good or bad, image quality, and these attribute labels, they prove to be a valuable signal for a subgroup analysis and for generalization into the wild deployment conditions. Another thing, accuracy. So to check the accuracy of our annotations, because still, well, there is some human error when we label. Moreover, it's a bit ill-posed because we have only single image, right? But we decided to show what is the trade-off of inaccuracy with our methods. So we calculate the accuracy of the face shape reconstruction compared to ground truth scans. So our labelers also labeled the images from already well-known data sets that were captured not really in the wild. And we explicitly validate the accuracy on neutral images only, because the 3D scans do not capture motions, as I mentioned. And we also check same thing for pose estimation on such benchmarks like BV, for example, and report the error of our annotations. And we show that they are good enough. There exists a known trade-off, of course, in accuracy, but the performance is sufficient for many applications that operate in the wild. So that's it for accuracy. And the last D stands for dense. So DAD 3D heads dataset is dense. As I mentioned, we have more than 3,500 verified landmarks for training different models, localizing many more than your usual 68. And this flexibility, it saves the human annotator efforts, because if you have to have a different setup next time, you do not need to relabel the data. It was labeled once, and then you just select the subset of the landmarks that are of interest for you, and that's it. There you go. Okay, that concludes the dataset part. Now let me move on to the model really quick, DAD 3D net. So our goal is to estimate a compact 3D head representation from a single image. And so having our training data, we can train an end-to-end model that predicts a vector of 3D parameters and a dense set of 2D landmarks. So we do it in the multitask fashion. And well, here's the architecture of our model. We have a pre-trained CNN encoder. You can be flexible with respect to that. We used ResNet 50. It can be actually any, depending on the setup, deployment requirements, etc. Then we have the Gaussian heat map estimator that predicts coarse locations of the head landmarks. Then we fuse them together with the CNN encoder output and by FPN feature maps to encode multi-scale representation. And from that, we regress the 3DMM parameters set, and finally, like finer locations of the head landmarks. We, of course, incorporate differential flame layer as our final mesh is in flame topology, that this layer would map the 3DMM vector to the 3D mesh vertices. And that's it. As for the training, we try to address the problems of shape reconstruction and pose estimation simultaneously during training by optimizing with several loss components. So the shape and expression loss, it's based on the normalized 3D vertices. So we don't care about pose there. And it enables to disentangle the shape plus expression from the pose, while the latter is based on the full head dense 2D landmarks, and it's a reprojection loss, and it assesses the pose accuracy. And that makes the rich annotations fully utilized, which could not have been done previously due to the lack of ground truth annotations that we have. And then moving to the final contribution, the benchmark. So we propose the benchmark to evaluate the task of 3D dense head alignment from an image. Basically, we measure the goodness of fit. We measure the pose fitting and also face and head shape matching. So we have two metrics that are normalized mean error of the reprojected 3D vertices onto the image, and ZN accuracy that I will talk a little bit more about, because that's probably the most unknown one. So that one evaluates, we introduced that one, and it evaluates the ordinal distance of the Z coordinate and accuracy of the 3D fitting. Because as you might argue, and rightfully so, our annotation scheme, it's only conditioned upon the model prior and the reprojection onto the image. So we cannot really guarantee the absolute depth values to be as accurate as on sensor data, of course. And that's why we address this issue by measuring the relative depth as an ordinal value of the Z coordinate, because maybe we cannot guarantee how perfect the absolute depth is, but we definitely can tell that the frontal part of the face is like more in front than the back of your skull. And we compare those relative depths of landmarks, and 5 stands for the subsets that we compare over. And well, we believe that this benchmark is really beneficial for the community. At that point, we just hoped that it would prove such. As we can see now, 2 years after, there are multiple research papers that build upon it. And yeah, the need for this benchmark was because the 3D scan-based shape reconstruction benchmarks, they're indeed very accurate, but they cannot capture emotions. They're not really in the wild. Yes, of course, they provide community with accurate neutral scans that correspond to not necessarily neutral input images. So there is this a bit of discrepancy. So one cannot really measure how well the head or face is reconstructed with expressions that are included into the mesh. So we're trying to fill in this gap. And as for the pose and rotation, in the paper, we show more like visuals for some label inconsistencies in some of the in the wild data sets, or in other data sets like BV, they're in the lab. So again, we try to fill the gap for the benchmark that will be both reliable, at least within a known error that we measure, and they would be in the wild. And last thing, I want to talk about just like some applications, how people build upon it, upon those 3 main pillars of the paper. So, for instance, there is a very recent paper that is accepted at CVPR 2024. What they do is they train on the D3D heads data set. They also build a new metric to benchmark on our data set. So, for example, they say that, okay, normalized mean error, indeed, it's very widely used by lots of the methods to check how well they perform, but it's very sensitive to how people choose the landmarks to evaluate upon. While what they do, they try to be agnostic, and they just pick, okay, what is the capacity of the subset that they want to measure upon, and then they check upon all of such subsets of this capacity and check what is like the best fit, the minimal fit. Then another paper of actually one of my co-authors on this project by Orest, who is now a PhD at VGG Group. So it's still not released, but very soon to be. What he's done is generating synthetic data, and he uses in his generation pipeline the off-the-shelf DAD 3D net. So yeah, they create large-scale synthetic data set, and they perform the image generation process with latent diffusion model that would be conditioned upon 2D body pose and scene description. And then they have the binary detection model that would predict head bounding boxes. And then they have the 3DMM regressor, the off-the-shelf one, DAD 3D net, that would generate the final annotation for each head crop. So that's great. And another thing how people build up on our work, I've noticed personally, because I quite often check, okay, what is the new research that built upon DAD 3D heads? Mostly people liked the part about head pose estimation. So if we talk about benchmark, I see that mostly people measure on that part of the benchmark. And yeah, so they can create state-of-the-art models and check how well they perform on our benchmark. And especially, I see that it's very beneficial that we have this subdivision into subsets of different attributes, and gives really very good understanding and representation of, okay, what are the failure cases, what are the limitations of methods, etc. Great. Yeah, so I'm almost fit in time. So you can access our code model and download the data, of course, through the QR code. And thank you very much for your attention. And I think we can move to Q&A. I'll leave this slide just in case. And yeah,
thank you, Tetiana, very much. Are there any questions? Actually, we encourage all participants to ask questions in the chat or on Slido. And currently, I don't see any questions, but there is a chance to ask if anybody wants to.
So maybe can I maybe ask first question, Rostislav, is that okay?
Yeah, sure.
So Tetiana, thank you very much. Very nice work. I will ask a question about video. Like it seems the work is most focused on still images. Have you thought of extending a video? Would it be important for some applications, or maybe you was already in the pipeline? Can you say a few words about it?
So we, of course, ran some demos, but just like frame by frame to see how well it performs on images. Of course, as long as the images, sort of like the lighting conditions, for example, don't change too much and there are no some crazy occlusions or so on, they actually look quite well and quite smooth, even though it's frame by frame analysis. We did not really work on extension to videos because we wanted something very lightweight for the applications in the company, and what we needed was mostly just the single frame stuff. That would definitely be interesting because, of course, there can be the jitter, the inconsistencies as you move from frame by frame, and especially the problems occur when you have like rotation of the head. So side poses are good, indeed, but as you go to absolutely like backward position, of course, it starts working not that well. So that is a huge limitation when we would run demos on videos for sure. But as for because you said for the method to work on videos, or also the data set to be not
both. I think, of course, the method, but I guess one may need some data for a video to make.
I think that it would be really complicated to label, at least that particular proprietary tool. It was not really well suited for labeling videos for sure. And yeah, that would be, of course, great extension, but we definitely did not think about extending to on the dataset part. And for the model, we just never needed to, but that would probably be the easier path, just to work with pseudo labels and just to have the model that handles time consistency better.
Thank you very much.
Thank you for your question.
Great, thank you for Tetiana. There is no further questions, so let's thank Tetiana again.
Yeah, thank you.
And we are well.
I encourage you to use our data and benchmarks. Yeah, and contact us if you have any inquiries, of course. It's all on the project page. Thank you.
Thank you.
Thank you very much, Tetiana. So I remind the workshop participants that there is a Slido link, which is in the chat. You can even post your questions in the chat. We will ask them. And with that, I would like to introduce the next speaker. So the next speaker is Torsten Sattler. Torsten, thank you very much for joining us today. Torsten is a senior researcher at the Czech Institute of Informatics, Robotics and Cybernetics at the Czech Technical University in Prague. He's also a member of the ELLIS unit. And he's heading here the Spatial Intelligence Group. Before joining CIRC, Torsten was an associate professor in the Department of Electrical Engineering at Chalmers University of Technology. Before that, he was at ETH Zurich at different positions, starting first as a postdoc and then as a senior researcher, working closely with Mark Polface. Torsten, just to complete his bio, obtained his PhD from the RWTH in University in Aachen, and under supervision of Leif Kobalt and Bastian Leibe. Torsten is one of the program chairs of the current ECCV, so we are all waiting for the decisions now. But Torsten, thank you very much for this work. Organizing conference is a huge amount of work, so thank you very much for that. But today he is going to tell us in this workshop about he's doing some very exciting work in 3D computer vision. He's going to tell us about building 3D models for visual localization. Torsten, thank you very much for joining us. The floor is yours.
Thank you very much for the invitation. It's a very nice introduction. I'm going to talk about two papers that we're actually going to present at CEPR this year. I'm going to start with the 3D model building part, and then talk a bit about visual localization. So the current hot topic in 3D reconstruction is probably 3D Gaussian splatting. This was a SIGGRAPH paper last year. This is their result. So this is real-time rendering of a scene reconstructed in Gaussian splatting. As you can see, it is able to produce photorealistic results. And the way that this works is that the scene is represented as a set of 3D Gaussians. And each 3D Gaussian is essentially the mean, which is position of the Gaussian in space, a covariance matrix that encapsulates the size of the Gaussian, a function that models how the Gaussian appears or the color of the Gaussian appears, depending on the direction from which you're looking at it, which is typically like represented by spherical harmonics in order to avoid having to evaluate a neural network, and some alpha value that corresponds to occupancy or transparency, how transparent or non-transparent the Gaussians. And rendering it is quite simple. If you want to render the scene, you sort the Gaussians front to back as seen from the camera. And for rendering, you just you essentially splat the Gaussians. So you project the Gaussians into the image and then alpha blend the colors in front to back order until your occupancy is large enough that you can say nothing behind this will happen. And this is very similar to volumetric rendering in NeRF, but has the advantage that it's much faster. You don't need to evaluate neural networks, and you can use rasterization for the rendering, which is how traditionally GPUs have been built. And this is still much faster than doing ray casting or ray tracing. Conceptually, the thing works algorithmically. You start with a set of 3D points. Typically, the scene is you get the camera pose that you need to construct the scene from structure motion. Structure motion at the same time gives you a sparse set of 3D points that you can use to initialize the Gaussians. So you end up with a set of Gaussians, and then you have a training loop where you, for a given training image, you project the Gaussians into the, or transform it into the coordinate system of the camera, project them, rasterize them to get color. So you get an image that you can compare to the actual image, and then backpropagate through the projection to modify the properties of the Gaussian, so you can adjust size, position, color, and so on and so on. And the second one is, the second backpropagation is to some density control mechanism, where the idea is that if you have a region that's under reconstructed, you are starting to create or spawn more Gaussians in that area that you then optimize so that you properly reconstruct it. If you over-reconstruct, meaning you have like a way too large Gaussian, you split it and then also optimize it. So as I showed you before, this can work really well, but it also has a couple of issues. So let's delve a bit into this. And this is the work that we're going to present at CVPR. We got lucky enough that it was selected as an oral, and this is really the work of Sehao Yu. And so this illustration here is you have a 3D object, which is represented as a Gaussian, shown here as a split through this 3D Gaussian, and that's then projected. The projection is again a 2D Gaussian, and you get a color in the pixel of your image. 3D Gaussian splatting tends to generate many small Gaussians because it wants to be able to recover fine details, such as the spokes of the wheel of the bike that we saw, or this many small leaves. That is a bit of an issue because many small Gaussians can lead to numerical issues and make the optimization harder. And what the paper does to be able to have a more well-behaved optimization problems is actually tries to ensure that there's a minimum size of the Gaussians in the images. And this is done using a 2D dilation filter so that you ensure that the projection has a certain size in the image, which is actually something that's not described in the paper, but it's done in the code. And this leads to a couple of potential problems. So first of them is if you decrease the focal length or move away from the scene, then because of the dilation, small things that should project to like a small, like 1 or 2 pixels, get larger, or should project within a pixel, get larger because this dilation operation makes them larger in image space. So here the spokes of the bike appear larger than they should be. It can also lead to degenerate Gaussians. So here's like a Gaussian that essentially becomes infinitely thin. For the training images, this is not an issue because the dilation operation makes sure that it still covers the pixel. But if you zoom in, so if you increase the focal length, or if you move closer to the scene, you start seeing all these high frequency artifacts, which essentially come from tiny Gaussians that now get projected to a wrong size because the size of the Gaussians was not correctly estimated. Luckily, there's a principal solution for this, which is what we call MIP splatting. So the idea is what causes the problem is very small Gaussians, which correspond to high frequency details. And there's a very principled ways of handling issues caused by high frequency function or high frequency details, which is to apply some sort of low pass filter. And you can do this in 3D. So if you have a degenerate Gaussian, you can apply a 3D smoothing filter that essentially enlarges it, meaning it removes high frequency detail and then gives you a better projection. And similarly, we could do a 2D Gaussian filter, which is inspired by this physical box filter that you have in the imaging process. And that helps you to get rid of aliasing. So here's a comparison of the impact of both filters. On the left, you see the scene zoomed in without a smoothing filter. And on the right, you see this with the smoothing filter. As you can see, it leads to visually much more pleasing results because it removes a lot of high frequency artifacts. Similarly, this is without the 2D filter on the left and with the 2D filter on the right. As you can see, if you zoom out, which is farther away from the training pose distribution, you get aliasing effects without the filter, but with the filter, it looks much better. Of course, if you zoom in, which is close to the original training poses, then both of them have high detail. Good. So here's a side-by-side comparison of the original Gaussian splitting and MIP splitting. And as you can see that if you are starting to zoom in to the scene, then the original Gaussian splitting has problems properly rendering fine details, versus our approach is able to actually handle this. And the nice thing is this, like rendering-wise, this doesn't come at any higher costs. This is, you can still run this these renderings that are shown here in real time on a smartphone in the web-based app. And if you want to play around with this, we have code available, easy to install, easy to run. If you have run Gaussian splitting before, this should be really simple for you. Good. So this is the first part of the talk. Now let's assume that we have built all these fantastic 3D models, photorealistic and whatnot. What can we do with it? And that brings us to the visual localization problem. The visual localization problem is, given an image and some 3D model of the scene, we would like to compute the exact position and orientation from which this image was taken. And localization has many applications, augmented reality, robotics being two of them. And traditionally, and still a way to get high quality poses, is to run a feature-based approach. So you have a sparse 3D model that you get from structure from motion. Each 3D point is generated from 2 or more images. It can be associated with local features. If you have a query image, you extract local features. So you detect key points, compute descriptors. You do 2D, 3D matching by essentially comparing the image descriptors for the query features with the image descriptors of the 3D points. And then from this set of 2D, 3D matches, you run pose estimation. So ransack inside endpoint pose together with an endpoint pose solver. But this is like a very specialized representation, right? It's catering to the localization task. But if you think, for example, of a robot needs to actually perform more tasks, it needs to do path planning, it probably wants to interact with the scene. So a more general representation would be to have like a more dense representation, a mesh, Gaussian splitting, nerves, whatnot. And the question that we looked into in the second paper, which is the work of Andrea Vedaldi, is how can we use these meshes or representations in a render and compare framework. So the idea here is that for a given query image and some scene representation, we assume that we have an initial pose estimate. For example, GPS, or if you run an image retrieval step, the pose of the most similar retrieved image. And then you can render the scene, you can compare the rendering with the actual image, and then try to update the pose estimate so that the rendering better matches the actual image. And you typically do this in a few iterations, and then hopefully this converges to the actual pose from which the image was taken. And the main question here is, how do we actually do this comparison? How do we compare a rendering of the scene with an actual image? If you are just given images and don't have a representation yet, you could actually jointly train like a 3D representation of the scene and features. So if you have a query image, you run it through some encoder that gives you a set of features. You render the scene from the initial pose. So you could either render color, or you could render a set of trained features directly that are consistent with what the encoder gives you. And then you compare these features pixel by pixel and try to compute an update so that you get a better alignment. But of course, this only makes sense if the representation is not given, and you would need to compute it in anyways. But often you already have a 3D model that you would like to use. And what we discovered, or what the paper is about, is that pre-trained features are actually working very, very well in this scenario. So it has been known for some time that dense deep features can be used to give a good estimation of perceptual similarity between images. What we observed in this paper, that this perceptual similarity can actually be translated to pose similarity. We also observed is that the depths at which these features are extracted from a neural network correlate with the sensitivity of the cost function that allows us to refine the pose. So here's an example. What you see here is we change rotation from the ground truth pose and then look at feature similarity if we change the yaw or the pitch angle. And using coarse features, so features extracted from a deeper layer, gives you a very nicely behaved cost function that has a minimum close to the ground truth pose. If you go to mid-level features, so features a bit higher in the stack of the neural network, then you get a much more shallow pose, a much more shallow cost function, but also with a much finer, better defined peak. And similarly, if you use low features from earlier layers, you see the same thing. So we end up doing some hierarchical scheme where we start with coarse features and then have a second refinement stage with more fine-grained features. What's quite interesting is that these pre-trained features are actually quite robust to domain changes. So on the left, you see a real query image that we're comparing against a rendering of a textured model, a rendering of a model where we just have vertex colors. So this is some form, think of it as some form of smoothed out texture, and a rendering of raw geometry. And you can observe that you still get a very nice local minimum for the ground truth pose, but the value of this feature distance changes. And obviously, if you have raw geometry which looks different, the minimum is at a slightly different feature distance. But still, the behavior is the same, so you can use the same features to align an image to different types of models. Yeah, and that brings me to the last slide of the talk. So a bit more technically, we use pre-trained features inside a particle filter, which works very well and can used either as a localizer on its own. So starting from a pose given by image retrieval, you can do render and compare to get a more fine-grained pose. Or if you are given a pose estimate in the context of feature matching, you can actually refine it. So assume that you are given a more detailed pose estimate that you get from 2D, 3D correspondences, for example, then ours still allows you to improve on the pose estimate. Similarly, we observed that you could actually do like a few steps of this particle filter from an image retrieval pose, render the scene, and then do feature matching, and you would in some scenes drastically improve your results. There's a detailed evaluation in the paper, not going to go into detail, with multiple features, and we will hopefully soon release our source code. And with this, thank you very much for your attention.
Thank you very much, Torsten. Thank you. Are there any questions on the Slido, or please, feel free to put them in the chat if you have any questions for Torsten. For the other speakers, you can ask. You just raise your hand, and you can ask you can ask a question. I'll maybe start with the first question for. We have a question in the chat. Maybe I'll just read it out. Is it possible, asking someone called Jaspreet, is it possible to reconstruct the object when some parts of the object are in motion, e.g. to reconstruct the leaves of a plant when the wind is blowing? And if not, then what do you suggest to make it work? Great question. I had similar question on dynamic scenes. So Torsten, dynamic scenes.
So if you have like smaller motion, so leaves blowing in the wind, then this should work out of the box, but it will give you something blurry because you're essentially trying to find an explanation that works for slightly different projections. At least that's my experience. If you have larger moving objects, then this causes issues. So, for example, if you have pedestrians moving through the scene, you will actually see ghosting artifacts where it tries to reconstruct the same pedestrian at multiple positions. There's two ways to handle this. If you're actually interested in these dynamic objects, there's a 4D variant of Gaussian splatting, which actually tries to model this time dimension. Otherwise, if you're actually only interested in the 3D geometry of the scene, you can try to figure out during the reconstruction process which parts of an image correspond to moving objects or other occluders that are not there permanently, and then remove the contribution of this these pixels from the loss. We are currently working on something like this. Like for the follow-up question, whether it's possible to restore fine details, you could put, what I would try is there was some work on using diffusion models for super resolution in the context of 3D Gaussian splatting. I would expect that you can do something similar to this for slightly small, like for slightly blurred regions that come from small motion. Of course, this will not be, like, it's not necessarily multi-view consistent, but I mean, we're talking about an effect that is not multi-view consistent anyways.
Okay, thank you very much for the question. It seems the same question was in Slido, but it was already answered. Any other questions from anyone on this? Just checking the time. I think we have a little bit more time, maybe for one quick question. I will maybe ask Torsten then, what do you feel is the remaining main challenge in localization like related to your second work? Like, do you think it's kind of getting, we are almost there, or it's still far from solved?
I think like getting to the accuracy that you would want for augmented reality is still an issue. Making it run fast enough on an edge device is an issue. Making it compact enough to fit representations on an edge device is an issue. Making sure that if you don't want to run it on edge device but on a server, making sure that you're not revealing privacy sensitive information is an issue. So I think like this basic technology is kind of there, but making it robust, reliable, accurate, privacy preserving, that's still open.
Okay, thank you very much. Thank you very much for this very nice talk. And I guess there is a question on one more, but we don't have time for it. So maybe we will post it on Slido. Maybe Torsten can look at it, maybe answer online on the Slido. We are moving to the next speaker. So Torsten, thank you very much for joining us today again. And we are moving to the next speaker. And I'll ask here Rostislav, please, to introduce the next speaker. Thank you.
Thank you, Torsten, for a nice talk. And I'm very happy to introduce the next speaker. It is Igor Krashenyj. Igor will talk about one of the projects that was also reported on CEPR conferences a few years ago, and the advancement since then. So Igor got his PhD in biomedical engineering in Kyiv in 2017. He joined the Ukrainian Catholic University several years ago and teaches computer vision at master and bachelor programs, also co-advises PhD students. And Igor's research interests include computer vision, machine learning, biomedical imaging, among others. And I'm happy to pass the floor to you. So floor is yours, Igor, please.
Thank you very much for introduction and for this opportunity to talk. So today I'll talk about our work that was published on ECCV conference, not CPR. Let me correct you. So it's about fast, efficient, accurate, and robust visual tracker. This work was published also while we were working with Tetiana at Pinata Farms company, and basically the most of authors here the same as at DAD 3D heads. So visual tracking formulation, probably the most of you know, but let me to repeat it. So visual object tracking and visual tracking, it's a bit different things, because you could track points, you could track planes, but for objects, it's a bit different. So you need to be robust to reappearance, to the occlusions of the object. And so the task formulation here is the next, that having the search image and the template, we need to match and to predict and to understand the location of the object on every frame. So applications includes, but not limited to, the autonomous vehicles, surveillance system, robotics, augmented reality, video editing, and whatever. So it's everywhere, and a lot of applications are used, like for single object tracking and for multiple object tracking. But here we will talk about the single object tracking. So the motivation here goes from the need that the most of trackers are like not robust enough, not efficient enough. They sensitive to scene change, to background distractors, to reappearance. At the same time, it badly perform on unseen objects or on mobile devices. So the most of benchmarks that were constructed before, they not include the efficiency on mobile, since a lot of applications currently are moved from the cloud or from the dedicated hardware to mobile or to edge. That's why we decided to additionally to tracker itself, to create also a benchmark that will evaluate trackers and our tracker. Also, in terms of efficiency on mobile phones. So we benchmarked the current, at that time, state-of-the-art trackers, and they performed badly. So our tracker based on like Siamese neural network. The first Siam tracker was created in 2016, and basically had simple architecture based on the Siamese network, where we had like just a search image and the template image, and then extracting feature from both of them and searching on the search image the template. Another tracker that's similar to our work was Ocean Tracker, that had large footprint and inefficient on mobile. That's why like it performed badly and had slow inference. So it had feature combination, which like fuse the example image with the search image. So with like cross correlation there. And online update subnetwork that was introduced to keep the change in appearance of our object that we're looking for. Another approach that we benchmarked was Stark. It was a transformer-based tracker, which incorporated the transformer encoder and transformer decoder, and basically it was based on visual transformer. But it still had, it was not optimized for mobile usage. Another popular at that time tracker was LightTrack. But like the main problem of this tracker was that it had the optimization for the flops, but not the inference on mobile. So lower flops not always, it appeared, not always gives speed on inference and footprint for memory consumption. And also, since the architecture here was quite simple, it didn't have any kind of mechanism that incorporate temporal information and online update into the features of the tracker. That's why it appeared our research goals that we want to develop tracker efficiency benchmark that will allow us to evaluate trackers against each others and their runtime on mobile phones, and design a framework for tracking, like to get like good results in resource efficiency and accurate visual object tracking. So what we did, we took a backbone, pre-trained one. We fed there 3 crops, like not crops, 3 crops. We got like search crop, dynamic template, and static template. So we took 2 templates and fed it through the pre-trained feature extractor, and then we got like 3 representations of different crops. Having this, okay, we got there this dual template representation module, which had pixel-wise fusion block that incorporate temporal information inside of the representations, and then on top of it we got the bounding box and classification head regressions. So basically we had like 2 towers to predict bounding boxes and classes for them. As the backbone, we used their FBNet. FBNet was a neural network designed by NAS Neural Architecture Research, dedicated for mobile device usage. So it was designed by Meta, and nowadays it's still really popular for mobile applications. But I guess it can be replaced by anything because like the framework is the same. The pixel-wise fusion block performs point-wise cross correlations to enrich the search features. So we get like search features, we pass them, and then we do the dot product with the temporal features, like template features, and heads. So they're basically just convolution layers which predict the location and the shift, like the shift from the initial position and the class of the object. So what's the most important here is this online update module, online update mechanism. So what we did, it was like basically learnable exponential moving average between the features of template, static template, and dynamic template. So by feeding it through the network, we were obtaining the representation, and in this omega or W parameter, we were learning it. So online update mechanism allows to propagate information about the object reappearance to the later stages of the tracking, and measure the cosine similarity to understand which like template should be used for a later stage. Okay, so how to train all of these things? So we had, like usually trackers, semis trackers are trained having 2 losses, like regression and classification head. But here we incorporate the triplet loss to regularize the embedding and representation of the crops that we were using. So benefit from the triplet loss here goes that we can, having this loss, use also negative props. So it's not only about it, which should reduce the amount of false positives. For the regression loss, we use the simple intersection over the union loss, and for classification, we used focal loss. What else? The tracker efficiency benchmark. It includes two protocols, online protocol and the offline protocol. The online aimed to simulate random real-time input stream processing, while the offline processed the constant number of random inputs. What we measured, we measured the inference speed, energy consumption, the throttling, and the thermal state of the device. So here is some figures of Ocean, Stark, Light Track, and our tracker, the FEAR one. So as you can see, the battery level, the drain of the battery of FEAR tracker is the best. While the thermal state also keeps, like, the temperature is quite low. Additionally, here we can see that the throttling is also like almost the same as for the Stark Lightning tracker, while for the Stark not Lightning we have like huge throttling. Tracker efficiency benchmark. We can see that the FEAR tracker benefits and outperforms the most of the trackers at that time by 30% at least on different CPUs and mobile devices. We did also evaluation on the standard tracking benchmarks such as VOT, GOT, LSOT, and NFS. So our approach showed good results on par with that time state-of-the-art trackers on VOT benchmark and also on par results on GOT, LSOT, and NFS benchmarks. So here you can see how it performed, giving like from the template image and different different frames from the frame sequence, and it performs quite not that bad. So we also did ablation study, which showed that dynamic template update, pixel-wise fusion block, and lower spatial resolution gives improvement to the baseline in terms of FPS. Somewhere like it harms to robustness, but still we were searching some balance between the robustness and expected average overlap and FPS. So the proposed tracker efficiency benchmark demonstrates an efficiency of current state-of-the-art trackers. So our tracker performs like it shows balance between the efficiency and accuracy on public benchmarks, and proposed network components demonstrate significant boost in both efficiency and accuracy. What else? Currently, we are exploring our tracker against new state-of-the-art, but not on RGB, but in other domains. So it appeared that since our tracker was trained on RGB, we have this bias of domain, and now we would like to evaluate like how performance of the trackers that were trained on one domain could be moved to the other domain, and like how to reduce this gap without retraining and augmentations, like how to reduce this gap and domain shift. That's pretty much it. Here you can find the code on our GitHub, and you can run and check how it works. Thank you very much.
Thank you very much, Igor. Very great presentation. Please ask your questions. And while there is, I'll ask the first one. Do you know of any other algorithms that used your tracker already?
I know that algorithms. I know that there's commercial use of them, but they're under NDA. But I didn't explore whether there's academic research based on this. But I know that in commercial use there are some.
Yeah, thank you. Please ask your questions. I don't see any. Let me check Slido, but I haven't seen it. Oh, there are. How do you deal with situations when the tracked object gets out of the frame and appears again a few frames later?
So since we have some kind of a bit of memory, we can get this back, we can expect, but we have expected appearance of the object, and we are cropping basically on every new frame. We have the expected area where the object should appear, and if it will appear in the same area, probably we will track it. But if it will appear from the other side of the frame, probably we will miss it.
Okay, thank you. There are a few other questions. I have reposted them on Zoom chat. So first, are there limitations for this approach, applications with different sensor modalities, infrared, ultraviolet, multispectral cameras?
How many objects? So which one of them? Or
no, that was the previous
I can see the previous one. The limitations. Okay.
Yeah.
So there shouldn't be limitations in terms of the data. So if we have this tracker was trained on RGB 3-channel images. So if we will just do simple retraining with the new data, probably we will get good enough results. But if the channel, spatial dimensionality of the data is different and we can't convert it directly, probably it will not be possible. But if we want to use the pre-trained weights that we have right now, it will be an issue. But if we want to retrain, it's not an issue.
Yeah, okay, thanks. And then the next one with how many objects can the tracker track and how computational cost increase?
Yeah, this tracker tracks, it's the single object tracker. So we can track only one object. And this is the problem of all single object, that each tracker tracks the single object. And multiple object trackers, they solve the problem a bit in different way. And as far as I know, if we in commercial usage, the most common approach to track multiple objects is to use VAD and Hungarian algorithm on top of all bounding boxes, or something like byte track or modifications of this tracker.
Yeah, thank you. And the last one, what are your thoughts and estimates on edge inference on microcontrollers? Would be useful for robotics and drones usage.
I guess it's all about like we have low I can't recall what exactly memory footprint does our tracker had, but I guess this approach could be squeezed in to something very, very small. As far as I know, this approach was used on edge devices, not on microcontrollers, but on Raspberry Pi. It's not the same, but still, it works pretty good in a real world environment.
Yes, thank you. Are there any last chance for the last question? If not, then let's thank the speaker Igor again.
Thank you.
And we are moving to the last speaker of this first session.
Okay, so thank you, Rostislav. I will introduce the last speaker. So we are very excited to have here Andrea Vedaldi today. Andrea, thank you very much for joining us today and sharing your work with us. A few words about Andrea. Andrea is a professor of computer vision and machine learning, a member of the VGG group at the University of Oxford. He is a recipient of 2 ERC grants and has served as a program chair of ECCV 2020 and will serve as a general chair of ECCV 2026. He is also a part-time research scientist at Meta in London, and he is doing very exciting work on the boundary of 3D computer vision and machine learning. And today he is going to talk about 3D generative AI from reconstruction to synthesis. Andrea, we are very excited to have you today. Thank you very much for coming. The floor is yours. Thank you.
Thank you for introduction. Can you actually see my slides? Not super clear on my end whether this is actually working.
We see slides, but it's in the present. We kind of see the presentation mode. Maybe you need to switch the screen.
Okay, let me try again. Yeah. Is this working better?
This is working.
Okay, great. Yeah, so thank you for introduction again. I'd just like to give you a glimpse of some of the work we have been doing in Oxford and in Meta about 3D generative AI. I'm going to talk a little bit about synthesis, problems like text to 3D, but mostly focus on reconstruction. So what do I mean by reconstruction? So suppose you're given a single view of an object. So it would be that image I0 to the left. And your goal here is to reconstruct a full 3D model of that object, okay? Now, that model we call M, and you can immediately see the problem. So there isn't enough information in that image to really perceive or estimate what would be the full 3D shape and appearance of that object, especially you don't see the back, right? You're missing that information for sure, but also the depth and the 3D shape will be, generally speaking, quite ambiguous. So what you really want to do here is to sample from a distribution of possible reconstructions. So there is a distribution P that is conditional on the image I0, and the variable that you want to sample is M, which is your 3D model. Okay, so that's what we want to do. Now, the way we're going to approach this problem is by using generating first a set of new views of the object. So what do I mean by that? So we start from I0, and then there is some model that is an image-based generator. Okay, this is not yet 3D, but this model is capable of generating additional views of the object we have, maybe one at a time or all together jointly. All right. And once you have that, you have enough now information that you can look at those views and try to perform a three-dimensional reconstruction of the object you want. And if you're able to do that, then you have solved the problem. Now we have a single image to 3D pipeline. All right. Now, why do we do that? Why do we have this sort of two-stage or two components design? Well, again, these two stages are, the first is a multi-view generator, takes an input image and produces multiple views of it. And the second one is a reconstructor mechanism, which could be learned or not. And the reason why we do that is that we could try to learn a model that directly does the prediction in 3D, but generally speaking, we do not have enough 3D training data for that. Instead, what we do is we fine-tune an existing large-scale image-based generator, for example, EMU model, if you're in Meta, and you fine-tune it to teach it to generate multiple views. Now, the advantage is that model is not 3D, but can be trained on billions of images and videos that we have available, all right? So it really acquires this information about the natural world, which is actually required to perform 3D reconstruction in a sort of open-ended manner, okay? You just don't have enough 3D training data to do that directly, I think. So here's an example. So this is a model that we call IM3D, which is going to appear in XML, I think, soon. And so what we did here was two things. The first was to note that if you want to generate these multiple views, it is actually better not to start from an image generator, but to start from a video generator. That the reason is that the video generator can generate several frames at once, and is also primed has already some experience of what it means to move a camera. So if you take that, we start from Emu Video here, again, because this work was done in Meta, and then we fine-tune it to generate up to 16 views of the object. Those are sort of views you can get, all right? Now, these look good, they're good, but it's not obvious that they're actually sufficiently 3D consistent to actually get a 3D object out. So these are just videos for now, just 2D. They look 3D, but it's not obvious that they would actually be good enough. But in fact, they are. So what we do here is we take a 3D Gaussian splatting. You already have a bunch of, so this was discussed previously in some talk today. So I don't need to go into much detail about that. Suffice to say that what we have here is a bunch of 3D Gaussians, which have a position, a shape, and a color. And those provide an approximation to the 3D scene we want to get, all right? And so then what we do is we take the images that we are available, either real images or generated images in our case, and we have a function which we call a rend, which takes this 3D Gaussians G and map that to an image based on the camera C, all right? So we have a camera, the 3D Gaussians rendering function that takes the 3D Gaussian model and generates a corresponding image. Once you have that, because the function is differentiable, you can put that into a loss, all right, a rendering loss, compare that to the image you actually have, again, generated or real, and then try to optimize your Gaussians such a way that it reproduces the views you have, right? This is, you can call this direct 3D optimization, right? So you have a 3D model, you fit it to the views you have, and essentially you hope for the best, okay? Now, this will fail or succeed depending on how good the views you have actually are. And because the views we are generating using this fine-tuned video model are actually quite good, it turns out that if you simply take those and fit directly a 3D Gaussian model on top of it, then you get models, 3D models, which are nearly indistinguishable. So you see here on the left, the original video, and on the right, the 3D model that we get out. And you can see that they're very close. If you look carefully, you will see that the 3D model is actually slightly blurrier. And this is due to the fact that the input views are still not completely consistent. Reason being that those were generated by a 2D model that has some knowledge of 3D, but not a perfect one. Nevertheless, this is very encouraging because this process of generating the video and then reconstructing the 3D object using Gaussian is actually quite fast, okay? But maybe you're not satisfied with that. And what we want to do is to put some intelligence in the reconstruction part as well. 3D Gaussians are great, but they do not really have a prior on how things are in 3D, right? Meaning you don't know what is the shape of a can of Coke or a cell phone, so you cannot use that prior information to do a better job at 3D reconstruction. So what you really do want to do is instead to use a reconstructor that is learned, all right? So here's an example from a very, typical model that has, I guess, taken our community by storm, as they say. It's called Large Reconstruction Model. It's from the folks in Adobe. And so what this does is a network which can take one or a few input views, right? So it works from a very sparse set of inputs. And using a very large transformer network can spit out a 3D model of the object, right? Now, this is better in a certain sense than 3D reconstruction using a direct approach, like just optimizing rendering loss, because it can incorporate in the network weights prior information about a data set, for example, Objaverse, which is a synthetic data set of 3D objects, about 1 million of them. And then you can use that prior information to do a better job at 3D reconstruction, right? That means you can work with the fewer views, okay? And second, you can also be more robust to slight inconsistencies in the input views you might have. For example, if those are generated as opposed to be real images. So that's actually quite useful for us. The downside is that it takes for them 385 GPU days to train this model. Now, if you're in Meta, fine, you can do it. If you're in Oxford, you can't, all right? And I really want this research also to progress in university. So what we did was to look for a class of reconstructed models that would be a lot more efficient than this. So that's why we introduced the splatter image, which recent work is going to be introduced, in fact, in CVPR this year. So what we do here is we take as input an RGB image, just a bunch of colored pixels. Then we have a UNet that takes that and spits out for each pixel the parameters of a 3D Gaussian, all right? And this is actually very fast because all you do to perform 3D construction is to run your UNet once, and that gives you the parameters of the Gaussians, 3D Gaussians you have to use to reconstruct the image. Now, to see this in more detail, so here we have a bunch of image pixels, that's the grid there, and we have a camera center. And then for each pixel, what we do is we shoot an array, and the network, just this unit, tells us for each pixel the parameters of the 3D Gaussians that have to go there, or the 3D Gaussian that has to go there. And that is the opacity sigma, the mean location mu, so the centroid of the Gaussian. The capital sigma would be the shape of the Gaussian. Then you have information about the color, say RGB or spherical harmonics. And then you have delta, which is an off-ray displacement. So the way this works is that first you get a sense of where the Gaussian should go along the ray based on its depth, which is being estimated by the model. And then you have an additional degree of freedom that allow you to shoot away from the ray. So that's displacement, which is actually very important. And then you also get the color and the shape of the Gaussian. And of course, you get that for all the pixels you have in the image. And that gives you a Gaussian mixture, if you like, which is your Gaussian splatting model. And with that, you can take a single view, you see here on the left, each one of these pairs of image and videos. And then you can reconstruct the object also at the back, all right? And the reason that why this is possible is because the model is learned. You notice that the reconstruction is a little bit blurry at the back because this is not a generator. This is a deterministic network. So that's the price you have to pay for the speed. But nevertheless, this representation is able to do a full 360-degree reconstruction of the teddy bears. And you can see this here working also for the hydrants, okay? In fact, it works for single categories, but it also works, more generally speaking, for dataset like observers. So this is, we train a model on observers, in fact, and we tested it on another collection of 3D objects, which is Google scanned object. And you can see that the performance is still quite good. Again, a bit blurry at the back, but still very encouraging, given that the method is actually very fast, right? So how is this even possible? I mean, we are reconstructing single Gaussian per pixel. So obviously, if you see something in the input image, you're going to reconstruct that quite well. But what about the back? Well, if you see here what the model does, it uses the pixels that belong to the background to hallucinate the Gaussians that would actually model bits of the object that you don't see. For example, you see highlighted here with the arrows, the leg of the chair and the wheel of the car that are the back wheel and the back leg that you do not actually see in the image, but the model tries to squeeze that information in the 2D image that is actually generating to try to model that part as well, right? This is how this works. So I'm a little bit crazy, and it did, I mean, to me, it looked crazy when I first saw that, but it actually works to quite a good extent, I would say, very surprising. And the good news here is that this model is way more efficient than other single view reconstructors. So here we show the performance on the y-axis. We have LPIPs, which is new view quality, reconstruction quality, and the x-axis we have GPU days. And you can see that the splatter image is a very good compromise between quality of the new view synthesis you get and speed, which you can get at. In particular, we can get fast rendering, very fast rendering, in fact, 600 FPS almost, but also faster reconstruction, 40 FPS, and most importantly, fast training. So this only takes 7 GPU days to train. So if you have 2 GPUs, it's going to take 2 days and a half, all right? 3 days and a half, yes. A bit too optimistic there. So yeah, so this is great because it means you can do these experiments with university resources. You don't need to be in Google or Meta to actually do this. And if you want to go beyond single object, we have a new work that we just submitted to some conference. So this is foreseen, is the same concept, but take as input a single input image and produces output a 3D Gaussian splat for entire image, for entire scene. We call this Flash 3D because it's actually very fast. And so again, so the input is a single image, and the output is a full 3D reconstruction of at least the part of the scene which is not too far away from the viewpoint you have as input. And it turns to work very well and to be very efficient too. Now, I don't think I have time to discuss this in too much detail, but suffice to say that the trick we use here is we start from a pre-trained monocular depth estimator. We don't use pre-trained models of a generator, so we don't use pre-trained image generator models, but we use a pre-trained monocular depth model. And on top of that, we add a little bit of additional layers of information that turn that into a Gaussian predictor instead. And one thing we did, which is different from splatter image, is that for each pixel, we predict up to 2 Gaussians, not just one, because we don't have this idle pixel from the background that can be used to model the parts of the scene we actually do not see, okay? And so here you see that in addition to predicting 1 layer, we predict, in fact, 2 layers per pixel, or potentially more. Again, this is the same image as before. So before we were predicting 1 layer, or 1 Gaussian per pixel. Now we predict with our network also a depth displacement, an additional depth displacement that pushes this next Gaussian further into the scene. And then we have a displacement of the ray. And again, we predict the color and the shape. And again, we do that 3rd time if you want. and predict another Gaussian. So now you can have more information predicted for each pixel that helps you to model the parts of the scene you actually do not see. In-domain performance is really good. So this is trained on Realistic 10K, which is a collection of videos of apartments, essentially. And is, suffice to say, state-of-the-art in the UV synthesis performance when it comes to reconstructing these videos in 3D using a single image as input. But most importantly, it's also very, very good at generalization. Because we are starting from this very powerful monocular predictor model, which is unit depth, then we get for free essentially very good cross-domain generalization. So we trained the model on real estate 10K, which are apartments. We tested directly on Kitty, which is out of domain, and the performance is still basically state of the art. Okay, so that's nice. And so you see here the performance in with the sort of cross-domain setting. So train on real estate and test on Kitty, we outperform methods or do as well as methods that are actually trained in domain on Kitty directly. So again, encouraging. And this is where really we want computer vision to go. We don't want to be restricted to one data set. We want open-ended models. So I think this is important. So what are these different Gaussians doing? Well, you see here in red, the first layer that models basically the stuff which is visible. And in green, you see the second layer that's trying to model behind occlusions. That's the message. And again, this is learned automatically by the model. Again, you see the downside of this, though, that the results where these occlusions happen are quite blurry because this is a deterministic model. The best for it is to regress to the mean where it doesn't see something. So this is something that would have to be overcome in the future. Still, this is enough to get you state-of-the-art monocular new view synthesis performance in these data sets. And this is another visualization of what these different Gaussians do. So you see the first layer is modeling stuff which is closer to the camera a bit. But in particular, if you see to the left, there is a wall. So the first layer is modeling that wall. The second layer is modeling the stuff which is behind that wall. Okay, that's another way of saying what this second layer of Gaussian is actually trying to achieve. Again, this is trained automatically. Again, a small ablation. So the input image to the left, the obvious baseline in which you just reproject the Gaussian using depth in the middle and flash 3 to the right. And you can see that what we do more than that is just to fill in the blank spaces, if you like. This stuff you don't see in the image, these additional Gaussians are able to put something there which is meaningful, although blurry. So to conclude, what I presented today were two methods for faster reconstruction from single images and some applications to single image reconstruction using diffusion models. The splatter images for single object, Flash 3D is for scenes. And I think the two key messages here is that these are high-performance methods that are state-of-the-art in some contexts, some settings, but most importantly, they're very efficient, not just at test time, but also training time, which means that if you do not have big cluster, you can still use this kind of techniques to try to play a part in this, I guess, what is new, exciting research area in modern 3D computer vision, where machine learning plays a major role. And again, you don't want to necessarily have to use hundreds of GPU to get there. With this stuff, you can actually do that with maybe just a couple. All right, that's all. Thank you.
Wow, thank you very much for a very nice presentation, Andrea. So again, I invite the workshop participants to post questions either in the Slido or in the chat here. I will start with the first one. It's more technical, Andrea. So how do you choose the number of Gaussians? Is always 3, or do you have variable number?
So we have 1 Gaussian per pixel in splatter image, and up to, I think in practice we use 2 per pixel in Flash 3D because you get diminishing returns that you can expect. Now, that is a fixed number of Gaussians, but that's an upper bound because the model predicts for each Gaussian opacity value, and it can and will, in fact, switch off a majority of Gaussians in practice. So the number of Gaussians you actually get is far less than the number of pixels, or number of pixels by the number of Gaussian you predict per pixel.
Okay, so it's automatically, because if it chooses not to have 1, it will just predict it's see-through, basically.
Yeah, exactly. And I think you can see that very well in the splatter image case, where you see that this is the stuff here. I don't think you can see my mouse, but the stuff with the black background, that's opacity. What is black means there is nothing there. Okay, and so you can see that a lot of pixels in the background, they don't do nothing. They're just, those Gaussians are switched off.
Okay, and just also technical. So this displacement field, is this device? It's so important. Like this even in the Gaussian splatter image, is this because to model the stuff which is behind, or is it because to correct imperfections in the calibration?
I think it's mostly to really fill this stuff in behind. So you can see here. So it's a bit difficult to see, but also because the images are a bit pixelated. But if you see the input image of the car, you see that there is where the arrow is pointing in the sort of purple image of the car there. That's actually off the car itself. And you can clearly see that it's trying to model a wheel there. It's a little circle. That's the wheel that goes to the back, right? And the displacement is needed because you have to put that wheel back, right? That wouldn't be on the ray, it would be off the ray.
I understand. Okay, very nice. I understand. Thank you very much. I'm looking into the Slido. I don't see any questions there. Katerina, help me out, please, if there is any questions on the Slido, or if there are any questions in the chat, please.
At the moment, I see none, but maybe
Okay.
people are taking time to write
If
it.
anyone wants to put a question, we have a bit of time for questions, so don't hesitate to put some either on the slide or in the chat. If there are, while we're waiting for more questions from the audience, I'll ask one more. What about dynamic scenes, Andrea? Especially in videos, they often are moving parts. Do you think these methods can go there, or?
Absolutely, that's exactly what we're doing now. So, yes. I think actually to put it in a broader context, I think the next frontier of 3D vision is 4D computer vision. So 3D vision is very important, I think, to summarize and understand videos because it compresses information. So, for example, it removes the confusion that is given by the fact that you might have a variable viewpoint. So compressing and understanding video in 3D is very important, but then unless what you're imaging is actually absolutely static and only the camera moves, then you need 4D understanding. So I think the next big thing will be 4D in the space of 3D vision. So certainly we are looking at doing 4D versions of anything we have discussed today. Yes.
Okay. So of course, so this is great. Any more questions? If there are still, yes, go on. Katerina, you lost you.
You're muted, Kate.
Katerina?
So the question inside was if you will share the slides with participants.
Yeah, I think it will be possible, but the meeting is recorded anyway, right? So you will be able to.
Yes. So there will be recording, but
yes, you'll have the recording of the meeting is also on the YouTube. So I think it should be there. And if there is interest, we can also ask for PDF of the slides of the speakers. There is a question in the chat. Marigold shows that you can use diffusion to estimate the depth. In the future, do you think you can have a pipeline with depth estimator together? I guess this would mean depth together. I didn't quite get it. If it's
I mean, I suppose you can, let's put it this way, you can certainly try to think about doing diffusion on top of splatter image. Yes. And that would also basically fuse UV synthesis, Gaussian splatting, and depth estimation, the single network. Yes.
Okay.
Yeah, that did not escape our attention. Let's put it this way. Yeah.
Okay, very good. One more question.
Very good question. Thank you.
I will also read it out. Dmitro Kushnir is asking, how about metric stability of this approach? Is it possible to maintain map and perform loop closure with this approach, at least in the future?
That's a good question. I mean, so this is estimating a single Gaussian splat for each image. Well, to give an analogy, Duster, for example. So it has this network that does 3D point cloud estimation given 2 images as input. But then there is another step, which takes the reconstructions you get from pairs of images and reconciles everything together. So I think that would be one way of doing it. So you can do this, you can get partial reconstructions with this, especially for Flash 3D that at the end of the day doesn't do a full 360-degree reconstruction yet. And then try to glue things together later. I think that's completely fine. I'd like to see a world where there is a network that does it all in one go. So but that's much harder.
And one more maybe question. It's a little bit more kind of speculative, but still would be great to hear your opinion, Andrea. So of course there's a lot of 3D computer vision and geometry we are building on over last decades of research. Do you think that with the learning, we kind of in the end we will learn everything? What's your kind of more view of where things are going?
Yeah, it's a good question. So one reason for me doing 3D and low-level computer vision in that sense, 4D, etc., is that I thought that was one of the niches where computer vision will last for longer in a way, as opposed to be absorbed in multimodal LLMs. Okay, so that's my guess, meaning that I think that we will survive for a while longer. In the long term, hard to say, really. Can you do a magic transformer that does it all? I would say no today, but difficult to say what's going to happen in 10 years.
Okay.
So yeah.
Thank you very much.
Yeah.
Or anything else you want to add?
No, I mean, I think to get there, there's still tons of exciting research you can do in 3D and 4D especially. We're not there yet. That's for sure. And until we get there, there's tons that we can do in terms of modeling and devising more efficient architecture for 3D and 4D, etc. That might actually stick around for a while, maybe for a long time. So it's a good time to be into this area, I think.
Okay, so thank you very much for your insights. I will maybe only add is that sort of course, 4D, the additional dimension is interacting with the scene. And then, of course, then robotics come in, and this is just like a link that the next section will be focusing on robotics, which, of course, is now we have machines which are interacting with the world around us. And with that, I would like to thank again to all the speakers of this session. It was wonderful talks. Thank you very much again.
Yeah, thank you all.
Thank you. Bye-bye.
Bye-bye. And we have a break. We have a short break now, and we resume in 20 minutes in 3 o'clock with the session on robotics. Thank you much. Thank you very much again.
Thank you for having us.
Bye-bye.
Bye-bye.
Meanwhile, I would like to announce ELLIS lightning talks at the coming 19th International Conference IC3 2024, which will be held in Lviv in September. And we invite lightning talks from the authors of recent papers with very inspiring topics. So please send your submissions if you want to participate, and or recommend anybody would like to listen to or spread this information among your colleagues.
So Martin, Saska is here. Martin, are you here? Can you hear us? If not, one possibility is that we will maybe start so that we can start. We will start with sort of the next talk, and if Martin connects, so we will kind of reorganize the program a little bit. So I'm just sort of looking at the program. Oh, but actually Martin is not, he's connected as the second speaker. Sorry, I had it wrong. So first start Ruslan. So, okay, so we'll wait for Martin. We'll start with Ruslan. So, okay, let me just start this next session. And then we hope that Martin Saska will connect. Sorry about this. Okay, so let's start the next session. So welcome to the second session of the ELLIS workshop on 3D computer vision and robotics. Again, I would like to thank everyone for coming, all the participants. And again, for the second session, we have a great lineup of speakers, and I would like to thank them very much for connecting, for joining us and sharing their work. I want to also mention, I think Rostislav has already mentioned it. I would like to sort of mention this briefly again, that we have this. We are co-organizing with the Lviv unit the ELLIS Lightning Talks track, which is going to be an online session at this IC3 conference, which is a local conference in Lviv this September. And for this track, we are inviting authors of recently published or accepted papers to give a short talk about their work. So this is sort of mainly targeted at sort of top-tier machine learning venues. The goal is really to share and have a discussion about the recent work within the ELLIS community. And we are sort of targeting researchers, students connected to Ukraine in some way. And because it's hard to travel for some of them, it's going to be fully online, and it's going to be a forum to discuss some of the recent progress in the machine learning driven areas relevant to ELLIS. But we welcome submissions also in other areas. So with that, let's then start the next session. I see Martin is online here, which is great. Thank you very much, Martin, for joining. So we'll start with the first speaker, which is Ruslan, but I let Rostislav to introduce him. Thank you.
Yeah, thank you, Joseph. Actually, I would like just to slightly comment on these IC3 conferences. It's not local, it's international, because the next 20th will be held in Nice. next year. So then let's start the second session of our workshop, and I'm very, very pleased to introduce Ruslan Partsey. Ruslan graduated from UCU, Ukrainian Catholic University. He got Master of Science, MSci degree in Data Science in 2021. Right now, at the moment, he is a PhD student in Computer Science in Lviv. But he's also already a head of Data Science Master Program. So he is managing all the courses, lectures, and organizes the program. His research interests are mainly centered around embodied AI, and he has very great collaboration with Meta and other colleagues from Georgia Tech, and probably even larger. And some of the latest features publications include CVPR submissions in 2022 and 2024, ICLR this year, and NIPS last year. And today's presentation is the brand new one, and it's based on the project which was accepted to the one of the CVPR workshops. And the title is "What do we learn from using text captions as a form of 3D scene representation?" So Ruslan, the floor is yours, please.
One moment, can you hear me?
Yes.
Yeah, thank you so much for the introduction. It's my pleasure to open this section. And I'd like to share with you some of our early results and basically what did we learn from using text caption as a form of 3D scene representation. And as Rostislav mentioned, this work has already been accepted to CVPR workshop, and it's been done in collaboration with Meta AI. So with agenda, we'll briefly cover like motivation, benchmark, and evaluation, an approach for one scene study, human study, and model study, then move on to experiments and concluding remarks. So actually this project was mainly motivated by the following three research questions. What information about the 3D scene should representation contain to enable LLM achieve human level performance? For example, specifically on OpenEQA dataset, is it possible to create such a perfect scene representation? How choice of large language models impacts overall performance? What is the context size of the best scene representation? And in this representation, I'll be using the following definitions. Perfect scene representation is the representation that contains enough information about the scene that with alignment enables LLMs to reach human level performance on the broad range of embodied AI tasks. The second one is the perfect scene caption is the form of perfect scene representation in the text modality. And assumption is that if there is a perfect scene representation, then it can be used to produce a perfect scene caption. For example, that text can be used as a proxy to represent the encoded information about the scene. And the second assumption is that all of you know how widely visual language models and large language models are used. And so that's why I skipped this, described it in my motivation slide. So basically, a couple of months ago, Meta released an OpenEQA benchmark, very extensive benchmark for evaluating embodied question answering. And maybe embodied AI is the study of intelligent systems with a physical or virtual embodiment. And I have a short video about this benchmark. Yes, so we are curious to know whether we can build a perfect representation for one scene. And we selected one of the scenes from the OpenEQA benchmark, the subset of the ScanNet dataset, basically the kitchen with the countertop, which goes around the whole room. And our study approach was following. So we were creating scene captions iteratively, each time improving them and enriching their level of detailization. And we're working independently, designing captions, and then comparing them and performing analysis to find out what ingredients work the best. So we started from the initial scene captions that listed all scene objects, and then moved to scene description, describing different relationships between them. And then after the series of experiments, we found that actually direction prompt helps specifying the point of view of the agent. Then since object list should be like full and contains enough attribute information, then we found out that to improve the scores for one scene to reach the top performance, we need to have relative position specifiers, like for example, to the left or to the right, and so on and so forth. And we were iteratively evaluating two types of models, of large models, GPT-4 and Llama 2 7B. And also for comparison, we were looking at Llama 2 7B. And as you may see, moving from like baseline caption, we were able to improve the performance such that the model on one scene could answer all the questions. And I would like to also note that the scene description was created without looking at the scene questions. So the next step was to find out whether actually this scales to all the scenes. So that's why we started the larger human study. So basically we selected more scenes, in our case 15. We defined the annotation protocol, we invited external annotators and scaled one scene study. But what we also do, we asked the participants to write the scene descriptions following our structured prompt. But also we asked them to write free-form scene captions. So first participants should describe the scene in a free form, how they see it. And after that, we were giving them the next scene and asking them to outline the scene following our structured prompt. And the third stage of the human study, where we invited another people and we were asking them to answer the questions based on the structured and free-form descriptions we received from the annotators, just to see what's the performance, human level performance on this task. And so what we found out is that actually large language models already performs compared to human level or even better on a text modality. And actually both GPT-4 and Llama 7B have a similar performance. And actually it didn't matter for models and people whether it was free-form scene caption or structure form scene caption. And also, for example, in OpenEQA benchmark, authors reported that GPT-4V achieved around 80%. So there is a clear gap. that human on video achieve around 80%. So there is a clear gap between text modality and visual modality. So then we were curious to study models, whether they can leverage our studies result from human study and one-scene study. And what we were doing, we were like sampling some frames from the video sequence, then passing them to the visual language model and receiving captions. And then we were using those captions to feed into large language models to estimate how they perform. And so we evaluated a couple of models based on the previous studies, and we evaluated them in 0-shot, 1-shot, or 2-shot prompts. And we were also using variable number of frames, 5, 10, and also we were experimenting with different frame selection algorithms. By default, OpenEQA benchmark, we're using like uniform sampling, but we were curious whether some more fancy frame selection mechanisms could improve the overall performance. So as you may see on the right, actually the scores are pretty much the same. It means that large language models, unfortunately, currently are not capable to leverage enough context information. For example, given 1-shot or 2-shot examples, they are not benefit from it. Also, they really don't pay attention to the frame selection mechanisms, meaning that they're not capable to identify difference in frame selection. And also, the worst performing categories still remain special understanding for all of the models. So our human study shows that capabilities of text representations is bounds OpenEQA performance, that human achieve much higher level scores given videos than text. And also, obviously, large model types are better than small. But what we noticed is that all of these models, when they pass a certain performance threshold, their OpenEQA performance saturates. So, and we also tried to estimate the maximum total length of the representation. So we basically took as the way how we described objects in our caption, and then took average number of objects and multiplied by the approximate description length. And what we found that like by default, humans write twice much detailed descriptions that visual language models by default. And also we found that using few-shot caption examples to guide VLMs does not improve their generated captions. So basically there is clear gap between humans and models, for example, GPT-4 or Llama 2 on all of the forms of captions. Yes, and also that large language models already achieve the human level performance in scene understanding on text modality. Another interesting slide that we didn't include it yet into our project result is that GPT-4o that was recently released actually surpasses the text modality given multiple frames and shows very promising results. Unfortunately, we don't know the architecture details and evaluations of those algorithms. So this is pretty much it. Happy to answer the questions.
Thank you. Thank you very much, Ruslan. Are there questions? I don't see any in the chat or in the Slido, so please go ahead.
Maybe I'll ask one. So thank you very much for the interesting talk. I think these environments are, especially for service indoor navigation and interaction, it's important,
yes.
I think, for the progress. Yet my understanding at the moment, they are kind of more static. Do you think, is there a kind of, is there a way or is there a plan to include also make them more dynamic? That will also include dynamic scenes, moving objects, other moving parts. I guess there are moving parts you can interact with, but
yes, yes. To the best of my knowledge, is that most of the researchers is this domain focused specifically on like designing representations.
Mm-hmm.
And I don't know if you heard about concept fusion. That is actually the reconstruction based world representation, and all of the researchers want to focus on learned representation such that they could leverage semi-supervised or self-supervised learning, and also like scaling. And to the best of my knowledge, even designing a static representation that could improve like across wide range of embodied AI tasks is not yet solved. So like dynamic environments, yes, but even static are not solved yet. And so maybe one example of the dynamic and where the community is moving is using kind of dynamic 3D scene graphs, but again, not yet solved.
Mm-hmm. Thank you very much. I tend to agree. I just wanted to sort of, ask, where things are going in terms of the environments, which of course are very important. Thank you.
Yes, any other questions? Maybe Ruslan, one question from me. Have you thought about a kind of semi-supervised approach to handle these textual descriptions and maybe summarization, so that
Yeah, so maybe I'll give a little bit more context into this. So basically, the open sourced and approach to enable language model to have this perception most popular is by aligning visual features into embedding space of the large language models. And to make this alignment work nice, we need to have a large amount of alignment data. So, and in case of embodied AI, and what we are using question answer pairs in text. So so that's why it's important for us to have, for example, nice textual representation, such that we can design a questions based on that, and then learn our alignment module. But this is one of the strategies. So, and we haven't been using like semi-supervised approaches yet.
Yes, thank you. Any other questions? I don't see any in Slido. So if no further questions, then Ruslan, thank you once again. Let's thank Ruslan. And
thank you very much.
With that, I pass the turn to Joseph.
Okay, so I'll introduce the next speaker. So I'm very excited to introduce Martin Saska. who is very kind to joining us today, even though he's traveling. So Martina, thank you very much. Can you try to share your screen, please?
Yes, I'm working on it.
I will keep introducing you. Don't worry. Yeah, it seems to be working. Yes, we see it. Yes, we see your screen. Okay, so I'll just say a few words about Martin. So Martin Saska received his master's degree at the Czech Technical University, but then he did his PhD at the University of Würzburg in Germany, within the PhD program of Elite Network of Bavaria. Then since 2009, he came back to Czech Technical University, where he founded and heads the Multi-Robot Systems Lab. He was a visiting scholar at the University of Illinois, Urbana-Champaign. He also spent time at the University of Pennsylvania over several years. He is an author of co-author of more than 150 publications in both robotics conferences and impacted journals. So Martin is doing very exciting work in drones and multi-robot systems in generally, really sort of heading a team which is one of the leading teams in this area, which is confirmed by his team winning several robotic challenges over the years, including contributing to the very strong performance of the CTU team in the very challenging DARPA Subterranean competition. So I'm very happy to Martin is here today. You already seen glimpses of some exciting work, and today he's going to talk about onboard AI and 3D computer vision for autonomous robots flying in demanding real-world environments. Martine, thank you very much for joining us today. The floor is yours. Thank you.
Thank you very much for a nice introduction, and thank you for inviting me here. Yes, as has been mentioned, I'm a little bit outlier here. In our group, we are working mainly on flying robots, and AI and computer vision is, let's say, maybe 20% of our work. But usually my presentation takes 1.5 hours, so it was quite easy to select slides related to AI and computer vision to fit into 20 minutes. So yes, as you can see in this initial video, there is many kind of drones, but we don't call them drones. We call them flying robots, because all these vehicles are flying independently without any operator. There is no pilot teleoperating the drones. That we have always onboard computer, onboard sensors, and all the computational task needs to be done on board. So this is also where we a little bit differ from most of the presentations I could see here in your conference, where you have usually much more computational power, so you can achieve kind of much more, but it wouldn't be useful for our drones because we have the resources that we have. And this is the difference between our approach to AI and computer vision than the classical approaches. As I've been mentioned, I'm leading a group of now 45 employees plus many students and many autonomous flying robots in Prague. We are focused on multi-robot systems, especially on flying robots, but not only. We have also autonomous boats and fixed-wing like airplanes, and we have also ground robots. But 95% of projects is on flying robots. As has been mentioned, we were quite successful in many multi-robot challenges. We are focused mainly on the challenges that are kind of deploying the robots in real-world conditions. This is where we are strong. We really want to always fly and operate the robots in the real world. We don't have even any flying arena in our group, so we are probably the only flying robotic group without any lab for flying indoor. I always want to push my guys to go to countryside. You will see also many pictures from forest, for desert, even lakes, so the real environment. And this will bring the challenges I'm going to tell you about shortly today. We are also closely cooperating with companies. This is one of our spin-off companies. We are focused at the university on basic research of flying robots, but we are able also to reach to products level. So we kind of have the experience with the whole chain, going from the basic research to the application-oriented research. So let me now focus on the short story I am going to present you today. It's about swarming in the wild. So this slide I have created, it's maybe now 10 years ago, when I applied for one of my gacha projects, where I wanted to get, or I proposed to get a swarm of fully decentralized robots flying in the real-world environment with high density of obstacles. We selected forest as such an environment which is challenging. There is no GPS. It's also challenging to communicate for the drones in the forest. So our assumptions were to have GNSS denied environment, no direct communication, the fully decentralized system, scalable, large anonymous groups of robots with high density of obstacles. That time, our motivation to avoid like GPS and communication was also because at that time it was not reliable, mainly the communication for us. But now you can see, I see that you have many students and attendants from Ukraine. You can see that how important is flying without GPS, or having possibility of flying without GPS and without communication. And we have started with this already 10 years ago. So we are quite strong, and our drones are really flying without GPS, and they are solving their mission. So as the first fundamental achievement we had to do to really be able to fly as a flock of birds or fish of schools in real world environment is relative localization. If you want to cooperate closely and fly closely together with other teammates around, you need to know where these robots are, or what is their state, in fact. So all the control approaches like formation flying, swarming control, they require such an information about the neighbors. And as I have mentioned, we need to achieve that using only onboard processing and only onboard sensors. We don't communicate. We don't have any computer base station. We don't have any connection to the cloud. We need to put a small microcomputer and do the job on it. We have been trying many different approaches, most of them by vision. We tried RGB patterns, black and white patterns to recognize the other drones. We tried CNN approaches to detect the drones, but they were working quite well in kind of laboratory conditions. That's why you can see a lot of approaches by many labs worldwide using this computer vision on board of drones for relative localization, but none of them is using it in the real world. We have proposed an innovative idea where we were using cameras with UV filter. Why UV? If you take a look on this graph of spectrum of solar radiation, you see that in the UV part of the spectrum, the intensity of solar radiation go down. It's because of an atmosphere, which is filtering out this part of the spectrum of the solar radiation. And if we put a filter that allows to go on the chip only this UV part of the spectrum, you will get completely dark image with some bright spots in it, which are the LEDs mounted on our quadrotors flying in the proximity. So this is the trick, how to provide extremely fast localization. About fast localization, we are talking about hundreds of frames per second. So our required frame per second is 600 in some applications where we are flying fast. And we need to process sometimes 4 cameras to get like a full field of view. So imagine that all this computation you need to do on a small chip on the computer, on the onboard computer. We are also capable of communication by this system, by kind of optical communication. Since our LEDs that are mounted on all of our drones are blinking with some frequency, we can change the frequency of blinking and send through this frequency changing some information. It's all, of course, only a few bytes per second, but it is required, for example, to send some command to the drones. We have also designed quite a unique system, which is fully open source for multi-robot systems, UAV stabilization, localization, flying. The system includes several controllers. There is MPC, PID, now nonlinear MPC, SE3 controller. There is also many sensors which can be integrated. Some of them are vision-based, but also we are able to integrate 3D LiDARs, 2D LiDARs, radars, 3D cameras, and many others. So we have already more than 1,000 registered active users. So in case you would like to play with flying robots, you are welcome to try it. It's quite straightforward. Our bachelor students are able to fly in a simulator within 2 days. So probably you as experienced guys, you will do it in a couple of hours. I have also selected few drones just to show you our flying robots, where you can see that we are using 3D LiDARs a lot, but we have also many cameras on board. We have 2D LiDARs. These cameras here are for the relative localization, but we are now using cameras more and more for localization of each of the robots. So we are creating maps by vision and flying and stabilizing the drones by vision. Why? Because we want to really get extremely small flying robots that are less dangerous and that are capable of flying inside of houses, in the forest, where you have really narrow corridors. And for such a flying robot, as you can see here, the payload is only 150 grams, and the 3D LiDAR is half kilogram, the lightest one. So that's why we are relying on vision more and more, not only for relative localization, but also for stabilization. These are first results of the first Gacha projects I have mentioned. So we achieved that like 7 years ago. Then it took some time to get it published. So it's in the journal paper 2022. But this particular experiment was like 7 years ago. And you can see that we are capable of flying inside of the forest, as we have promised. We are relying on onboard sensors only, onboard computational power, no communication, no GPS. But of course, there is one big problem. The robots are pretty slow. So this is the next challenge we are facing right now: how to fly faster. If we are flying far from obstacles, as you can see here, above a desert, we can do fast deployment. But if you are flying really close to obstacles, you have to do agile maneuvers. It's a different story. So these are some other experiments from the forest where we are flying during the night. Of course, this system works pretty well in night because it has active LEDs for relative localization. So let me briefly, for the second part of my presentation, I hope I have still 7 minutes, if I'm counting well. I have kind of selected some challenges that we need to achieve to be able to really do fast flying of UAV teams in the wild. So the agility, as I have mentioned, it requires nonlinear control. So we are now working on a nonlinear MPC with obstacles, which is quite challenging. We are probably the only group which is able to fly in the real conditions with onboard an MPC right now. But we are also working on fast perception. It is the echo navigation, which means the navigation of the drone, doing the SLAM kind of mapping and navigation in the map. And also the relative localization, because if you are flying aggressively, everything is blurry, you have many problems, and you need to completely redesign all your methods. We are also working on the reliability of GNSS denied localization. Mainly if you are flying with vision, you are very dependent on the features in the real environment. So if you are flying through the forest, it's quite okay. You have forest, trees around, grass, bush, you know, many features you can get. But imagine the deployment of the drones above the sand, flat sand, or above a water, where it's really hard to find enough features. That's also why many of vision groups are flying indoor, as I have mentioned. Even they are using a special carpet. Probably you could see it in videos of Davide's Karamuse lab. They have a special carpet with many features, visual features. But let's go to the wild. We are also focusing on long-range missions now because we are flying fast, so we can do long-range missions. So again, this is useful in Ukraine, as you can see now, these 1,000 kilometers flights. And we are focused also on heterogeneous system with different dynamics. I have to be a little bit fast. So here I wanted to describe you a very interesting approach we found, where the team of robots, the swarm, the compact swarm, can help the individuals that are in troubles and they have not enough features in their visualization thread. Here in this experiment, so I have to skip the details, but in case you'd like to see more, just go to the paper. So in this experiment, here we have 6 drones, and only 1 drone is using like optical navigation, VIO, visual inertial odometry. All the other drones are completely blind, and they have the only source of information, which is the relative position of the guy which is with working VIO. The motivation is quite obvious. We have managed, even here in such an environment, flying above a grass, flat grass, the same at the desert, that it's very easy to get to an environment where you don't have sufficient visual features. But sometimes some drones, they can see some bush, maybe some house, something, some camel in the desert. So they can use this information and provide this information for the rest of the group. But we were also thinking about a problem. Imagine that there is no one using VIO. So if you are working with flying robots, you know that if there is no velocity measurement available relatively to the ground, and you have only IMU and nothing else, your drone will crash in less than 5 seconds. So here in this video, the yellow guy is the one, or like here, all of them are without VIO, all of them are without GPS, without communication. The only sensor they have is the relative localization. But this yellow guy doesn't have even the relative localization. It's completely blind. So if I, oh, sorry. Here, no. Here I run the video, perfect. So here you can see that the yellow guy is going to crash in 5 seconds. Now it's done. But the blue team is still continuing flying. Why? Because they can see the relative neighbors, and they can use this information for stabilization of the group. They are drifting, as you can see, that velocity is not intended. It's a drift of all these IMU and localization sensors, but since they are kind of kept together, there are linkages between the drones, they will not crash. And just briefly, because I have last 2 minutes, if I'm not mistaken, Another interesting topic we are working on right now is relative localization of large groups. So imagine that you have not few robots around, but hundreds. You are really in the middle of the fish school or birds flock. Then you have to detect hundreds drones in a single image, and you have to do it 600 times per second, and you have to do it on a small microprocessor. So what we have tried to use machine learning to train the network in a way to provide us not all the neighbors, all the particles around, but a density of swarm around. And this is exactly the information which is used by fish or by birds. They don't see all the 10,000 enemies around, animals around, enemy they see. But they see only few, only 5, and then the density. So we have tried that, and it is working, and we are able to stabilize the swarm based on that. Okay, sorry, I'm really going to finish. These are just a few videos about flying extremely fast. So we have designed nonlinear MPC to control the drone in the wild, flying more than 5G acceleration. So it's close to F-35 jets, and flying more than 150 kilometers per hour. But now we are working on the perception. And the idea is to use machine learning and to use also new smart sensors, like, for example, here, event cameras. So here the event camera is used to detect the extremely fast flying robot. So this is slowed down 600 times. And you can see also that we are even able to detect the props as they are flying. So it's a quite interesting and ongoing work. So in case you have experience in that topic, please let me know, and I will be happy to cooperate on event-based cameras, machine learning for agile flying, how to get fast flying drones into the wild. So before finishing my talk, I have two more slides. This is a European project we got, and it's financing your experiments. So in case you are working on some interesting vision and you would like to apply for flying robots in forest whenever you like, indoor, let me know. We have funding for a drone to build, for people to help you, and we can do the experiment for you for free. So just let me know. And the last thing, we are organizing a summer school every summer. This year, we have already 220 registered students, and the capacity of the room is 240. So there is 20 more slots available, but I'm receiving registration every day, so be fast. It's really interesting. Summer school, we have a lot of lectures, and we will show you how to fly with real robots during 1 week, and you will do your experiment with real robots on Friday. So this was everything from my side. Sorry, I was a little bit longer than I expected. And yeah, thank you.
Thank you very much, Martin. That was a wonderful talk. I can only confirm the school is wonderful. They have really world-class speakers talking in the summer school. So let's go to questions. I see there are some questions appearing on the slide. We don't have much time, but still let's ask. So the first question, Oleg Dats, why do neural networks and convolutional networks often fail in real-world environments? Is the issue computational, or is the problem with generalization? First question.
A very good question, both. Mainly, in our case, mainly computational, because we have to use really small networks to be able to process the pictures fast. And if you have a really small networks, then also the generalization is the problem. And as I have mentioned, also the features, in case you are flying in featureless environment, and if we are talking about localization. If we are talking about the detection of the objects, it's mainly about the computational power.
Thank you. There is a second question. It's related to my question, which I had. So the question is, can you please elaborate on simulators, AirSim, Gazebo, and Sim2Real Gap? And it's related to my question, which I'll ask. You say only we do experiments outdoors. I think it's great to really work with outdoor, with like a real world condition. But then I was thinking about the experimental loop, because if you can only go outside. So I guess I was thinking maybe you do simulation first, then you go outside. Can you elaborate a bit more on your simulation aspects?
Yes, of course, you are right. I'm here showing only the cherries, right? But before the flying in the real world, there is like maybe 95% work in the simulators. So we are using Gazebo for like the control, 3D LiDAR simulating and all these sensors. For the vision, we try to use photorealistic simulators. But we are not like really vision experts. I have 4 PhD students working on vision, but as I have mentioned, we are like robotic vision guys. So in case there would be some real vision people, they would like to help us. Yeah, you are welcome. So it's really like that. We use simulators a lot, but with vision, it's the gap between sim to real is the biggest, because
Okay, so we are a bit over time, so let's thank very much Martin, Saska, Martina. Thank you very much for joining us, even when you are traveling. There is maybe one more question but maybe you can answer it in the chat if you still have a little bit of time. And thank you again, and let's move on to the next talk. Martina, thank you for a wonderful talk.
Thank you, and have a nice evening in Prague.
Thank you. So we can move on to the next speaker. So maybe if Tim, you can start. Martin will stop sharing, and then thank you. So we will move to the next talk. Oh, Tim, are you here? Yes, I see you. By the way, if it doesn't work, we can swap the talks and we can give you a bit more time to fix the issue.
Yeah, maybe that will help. Maybe I can switch to a different computer. Sorry about this.
Okay, so let's we give you a bit more time, and then Ananye, we can start with the last talk in the program. Ananye is here, great. We see, yes. We see your screen. We don't see you yet. At least I don't see you, maybe, but we see your screen. Oh, you're here. Excellent. So it seems you're ready. So I will introduce you. So we are doing a little bit of a swap in the program. We're now doing the last talk before the third speaker fixes the presentation issue. So the third speaker, we are very happy, and I'm very excited to have Ananye Agarwal here, who he graduated. So I'll say a few words about him. It's great to have him here. He graduated from IIT in Delhi with a BE Tech in computer science, where he also received a President's Gold Medal during his studies. He did then an internship at Microsoft Research in India, and he's now doing a PhD at Carnegie Mellon University, working with Deepak Pathak. He's doing really exciting work in machine learning for robotics. I think he has one of the most exciting robotic demo I have seen recently. So I'm really happy that he accepted to show us his work today. So Ananye, the stage is yours, and thank you very much again for coming and sharing your work with us. Thank you.
Yeah, of course. Thank you for the nice introduction, and I'm very happy to be here. So before I start, I just want to check that you can see my screen fine and the videos are okay. Hello.
Yes, everything is.
Right. Yeah, so I'll just jump in right away. So let's say you want to build a robot dog that can walk on any terrain. Now, in recent years, we have seen a lot of work with these legged robots, which can walk in challenging terrains. But the interesting thing is that all these robots are blind. They have no information about, they have no perception of the environment, so they can't tell if there's an obstacle in their way. So given this robust performance, a natural question arises: why do we need vision? So humans and animals have vision or use vision when they do locomotion. And why should we put vision into our legged robots as well? Now, the answer to this, of course, is that vision enables very precise and agile locomotion. So take a look at these scenarios on the slide. So on the left, you have these stepping stones in the river. In order to go over these stepping stones, you need to place your feet very precisely. And in order to place your feet very precisely, you need to know where the location of the stepping stone in advance. Similarly, for these very high stairs on the right, you need to be able to lift your leg on top of the stair before you actually hit the stair. And in order to do that, you should be able to, you need some kind of perception to find the location and size of the stair. So of course, many people have tried adding vision to locomotion. And the typical approach is to build terrain maps. And what a terrain map is it's a representation of the environment, which gives you the height at each point around the robot. But the problem is that it's very hard to do this in the wild. And these terrain maps often have a lot of noise. So for instance, they will have a lot of pose estimation drift. So the map will contain artifacts such as this trough, which is not actually there. So how do you deal with this? The standard way to deal with this is at training time to simulate a large amount of noise in the map. So on the left, you can see what the kind of noises that are simulated. And you can see that there's a large amount of noise added. And what this essentially leads to is it degrades the signal present in the map at training time. So the robot can't extract a lot of signal from the map. And as a result, it's not able to, the robot is no longer able to walk or is no longer capable of very precise locomotion. So for example, on these stepping stones on the top, you really need very precise information of where the stool is and how big it is and so on. And all this information is wiped out if you add a large amount of noise at training time. So in our work, we ask the question, do we really need terrain maps? We take a different approach where we directly couple vision and control. So we go directly from an image of the environment to the joint angles of the robot and completely skip this intermediate step of making terrain maps. And what this allows us to do is get very robust performance and also very precise locomotion on very challenging terrain. So this is the work I'll talk about. This is the first work I'll talk about. It's joint work with Ashish Jitendra at Berkeley, and of course my advisor Deepak. So I'll start with some result videos. So this is our robot dog, and on the top right, you can see what the robot sees. So it's just operating from a single depth camera mounted on its trunk. And the depth camera takes the depth image, sends it to a neural network. The neural network spits out the image completely end to end. And there is this is a hiking trail near Pittsburgh. It's called Highland Park. And as you can see, these stairs are super challenging, like almost as high as the top. This stair was actually out of distribution, so it's higher than any stair it has seen before, which is why it got stuck. But it learned this reflexive behavior where it can overcome even that up. Again, you can see it's super challenging slope, very muddy as well, or like it has a lot of loose mud, so the robot keeps slipping. Eventually, it makes it over. Again, a very high step, almost as high as the robot.
Get it down from the other side.
Okay, so let's let's talk a bit more about how we actually train this. So this is trained in 2 phases. In the first phase, we learn to walk, assuming that the robot has access to privileged terrain information. So what I mean by privileged terrain information is these scan dots. So if you look at these yellow dots on the side of the robot, so these yellow dots are fed to the policy, and the policy essentially gets the height at each of these yellow dots, and we call these scan dots. So in phase 1, what we do is we take the robot observations, which is just the joint angles and the IMU information, and also the scan dots pass through RNN and feed it to a MLP. And this MLP produces the next action. Now, note that a robot sometimes needs to change its gait based on the terrain information, based on the environment information. So for example, if the robot is walking in very slippery terrain, then the robot needs to move maybe more conservatively. If it's walking in very high friction environments, or if walking in very muddy environments, then it probably needs to apply more torque so that it can overcome it. And this information is captured by the terrain physical or the environment physical properties, such as friction, the mass of the robot, the motor strength, and so on. So in order to make the policy aware of this information, what we do is we make this into a vector called ET. And this vector is called the environment extrinsics vector. And this environment extrinsics vector contains information like the mass of the robot, the friction, the motor strengths, and so on. Now notice that we take both of these information, the scan dots and the terrain information, and we compress it to these 2 latents. So gamma T is the exteroceptive latent, which captures perceptive information about the environment, and ZT is the environment extrinsics latent, which captures physical properties of the environment. So both these latents then condition a base policy, which can modulate the actions of the robot. So if there's a stair, you want to change the gait so that the base policy raises its feet higher. And if, for example, if you're in low friction environments, then maybe you want to take smaller footsteps. So how is this trained? We train this in Isaac Gym, which is a large-scale GPU simulator with a very simple reward, which is just to track commanded velocity and also to minimize energy. So notice that we don't pre-program any gate motions. We don't have any central pattern generators. It's just a very simple architecture. Then we train on this set of randomized terrain, such as stairs, slopes, stepping stones, and so on. And after about 6 years worth of experience, which takes around a day to simulate on the GPU, we get these very natural looking gates. And this is all enabled just by scale, no gate priors, very simple reward function. Now that we have this policy, how do we actually deploy it on the real robot? Now, the main problem here is that there are 2 sets of information this policy relies on, which is not directly available in the real world. So the first is the scan dots. You can't directly observe the scan dots in the real world because you don't know the height of the terrain around the robot. And the second is this extrinsic information. You don't directly observe the friction of the ground. You don't directly observe the payload on the robot. So how can we deal with this? So the idea is simple. We train neural networks which estimate this just from observable data. So for the case of the exteroceptive latent gamma T, we can estimate this from egocentric depth, which comes from the depth camera mounted on the head of the robot. So we pass egocentric depth to RNN, which estimates the extrinsic latent or the exteroceptive latent. And this exteroceptive latent is trained with MSE loss, like error on the ground truth latent, which we observed from phase 1. Similarly, for the extrinsic latent, which captures the physical properties, the intuition is that we can infer the physical properties based on the robot motion itself. So for example, if you're on slippery ground, then your robot may move its feet very fast. If it's robot is on muddy ground and the foot is stuck, then you might have a very large error between your commanded joint angle and your observed joint angle. So all of this information can help you estimate the physical properties of the environment. So, sorry. Yeah, so essentially what this network does is it takes a history of the observed joint angles and tries to estimate the extrinsic latent. And this entire thing is trained in phase 2 with supervised learning. So the extrinsic latent is trained with error supervision on the ground truth latent, and similarly for the scan dots latent. So once we have this, we can just deploy this policy on the real robot, and we can get all these results that I showed in the previous slide. Now, if you look at a bit of analysis on the results, we can see that the robot learns a lot of emergent behavior. So for instance, if you look at the stairs that I showed, these stairs are actually designed for human height, and humans are much taller than this robot. So for this robot, the stairs are almost like obstacles or hurdles that it has to jump over. And how does it manage to do that? Another slide here shows the height comparison between other robots and our robot, the A1 robot. So the other robots which you might have seen, like Animal or Spot, they're much higher than the A1 robot. So stairs, again, are much easier for these robots. And on the right, you can see the kind of challenges that this robot faces. So when it's trying to climb up, the foot can get obstructed by the stair. And when it's trying to climb down, it has to go at a very high angle, and this can cause the robot to topple over. So we see that our robot actually learns emergent behavior to overcome these obstacles. In this case, instead of climbing the way humans usually climb stairs, it's learned to move its foot outwards, this abduction motion, in order to climb the stair. And again, we didn't reprogram this, but algorithm discovered it by itself through large scale. We also see emergent footstep planning. So here the robot is planning its footsteps, where to place its foot in order to overcome this stepping stone. And note that the robot cannot see terrain around its rear feet, so it has to remember what it saw in the past in order to place its hind feet. Let's summarize the entire approach. It doesn't have any predefined gates, and it's all end-to-end with a very simple result. Just driven by data-driven algorithm. And of course, we carried this robot around the world. We gave demos at the talk. So on the top left, you can see that there's the oral talk going on. And during the talk, I was running the robot around. And on the bottom, this is at CVPR. And if you look very carefully on the left, you can see very tall, like Mardi Gras performers. So everyone was like looking at the robot instead of looking at the Mardi Gras parade. So it was very interesting. And give a live demo.
So as soon as some height,
this is a live news in
just try to walk over them. So we have taken this robot to Highland Park. There's a very difficult trail behind the Highland Park.
So I'll skip this part because still out of time. Move to the next one. Right. So so now I showed you examples of locomotion, but the question is, can we go beyond locomotion? Can we do even harder tasks? So humans often go beyond locomotion. They do parkour, and notice that this parkour is much more challenging than locomotion. First of all, almost every human can walk on stairs and do simple locomotion, but parkour requires years and years of practice, and very few people can actually do something like this. Second, parkour is different from locomotion because these actions are very dangerous. When climbing stairs, if you make a small mistake, it's very easy to recover. But if you're jumping across large gaps like this, if you make even a small mistake, then you're going to fall, and it might be it's almost impossible to recover. So in that sense, it's a much harder task than locomotion. So in this work, we show that the same approach that I presented in the previous work generalizes or scales to also do extreme parkour. So the rough idea is the same, but instead of stairs and stepping stones, we change the terrain a little bit and add more challenging terrain for the robot. And as before, there's a phase 1, phase 2 training scheme. I won't go, there's some slight detail changes which you can see in the paper, but I'll skip that and go to the results. Here, we start with a very long jump. So this is almost twice the length of the robot. And if you notice very carefully, as the robot approaches the gap, it changes its feet placement such that it's optimal for jumping across the gap. It uses its hind feet to really push off and propel across the gap. And just after the jump, it tucks in its hind feet so that it's able to land properly. This is a very high jump, again, twice the height of the robot. So super challenging. And you can really see the emergent behavior that it has done. So it's using its hind feet to jump up, then using its front feet to pull itself up onto the obstacle. And since it doesn't quite make it up, it's using its hind foot to try again and again to make it over the obstacle. And I would note that this is really pushing the limits of the hardware because we burned a couple of motors while doing this experiment. So I think we've really squeezed all the juice out of this hardware that we do. I don't think the robot can go any further. This is the robot realizing the unseen combination of obstacles. It has never seen this combination in simulation, but it's able to generalize. Yeah, here are some results in natural settings. Yeah, if you want to see more details, you can check out the website. Yeah. If anyone has any questions, I'm happy to take questions.
Okay, so thank you very much, Ananye, for the very nice talk. Very impressive results. I haven't seen anything like this. I think this is really great. Thank you. There are some questions in the slides. Oleg Dutz is asking, how did you fix sim to real gap? Did you use real data for fine-tuning? Can you please elaborate on generalization to different terrain types not included in training?
So that's a good question. So we don't use any real data for fine-tuning. And the way we fix the sim to real gap is by domain randomization. So you have to choose a set of parameters to randomize in simulation so that the robot doesn't overfit to the simulation. So for example, you randomize the motor strength, which means like how effectively your motor is able to go to your set points, PD set points. You randomize your stiffnesses, your damping, you randomize robot friction, and so on. So there's a very specific set of, like, you have to randomize this set of parameters. And then what happens is your real world lies within the set of domain randomized simulations. And then the robot is able to generalize to the real world, if that makes sense. And then the specific set of parameters you can find in the paper. Can you please elaborate on generalization to different terrain shapes? So what I mean by generalization to different terrain shapes is that, so for example, if you look at stairs, so you would only see maybe like 10, 20 set of stairs. And these stairs will have some set of randomization in the height and the landing. Real world stairs you might not have exactly seen the exact set of real world stairs in simulation, but the robot is able to generalize to that different shape. But there's also a different kind of generalizations to completely different terrain class. So for example, I showed you a rock in the video where the robot was climbing a rock. We never simulate a rock inside the simulator, but because it has seen such a wide diversity of terrains, such as seen stairs, it has seen slopes, it's able to generalize even to something it has never seen like a rock. So I think that's very interesting, and that's what you see because of really large scale data. This kind of very interesting zero shot generalization.
Thank you very much. If there are any more questions, maybe we can do one or two or quick ones. I have a question about setting the goals. So these high-level goals, like where the robot goes, do you set that manually, or is that how is that done? How do you know? Yes.
So in the first paper I presented, we command the velocity. So we tell the robot to go what speed it should go at and what angle it should go at. The second one, the robot, so we do, like I said, we do two-phase training. So in the first phase, we manually specify inside the simulator, like if I go back to my slide, you see these red points. These points are some waypoints that we have manually annotated. But when we do this phase 2 training, if you look at the sort of the red box, we train a neural network to predict the correct direction from phase 1 supervision. So essentially what happens is the robot can choose its own direction. So in this case, we just tell the robot to go straight, or we just leave it going straight, and the robot can choose. Like for example, on this graph, the robot automatically goes left and then automatically because it knows that's the optimal way to go over the line.
But how do you specify that the robot should go across the obstacle course? Like there is some kind of it's like an end of the room, or?
Oh, you just set it to go straight. So the robot shouldn't deviate too much from the straight path, right?
Okay, so it's basically set it to go straight at the goal, and then it sort of chooses its own path through the.
Yeah.
Okay.
Yeah.
That's what I. Okay, there's one more question, quick one. There seems to be two things. Maybe we go quickly. What are the tools, approaches, simulators are there to work on locomotion on non-rigid surfaces, mud, tall grass, sand? Can you please advise?
So that's a good question. So again, here we don't. So right now, from what I know, deformable surfaces are very expensive to simulate. So we don't explicitly simulate deformable surfaces. But what happens is because of the large amount of randomization, the robot is able to generalize to deformable surfaces. So I don't have that video here, but what we observe is that if you put this robot on a foam, it doesn't fall. Like it's able to walk over it. And I think it's because of, again, this like large set of randomizations that we put in simulation.
Okay, thank you very much. There's one more question in the chat, but I will maybe ask you, please, if you can look at it and maybe answer it in the chat directly, because we are out of time. But thank you very much again in joining us and sharing about your work. So we are going to move to the last speaker of this session. So we are really pleased to have Tim Welschehold here.
Yeah, I hope this works now. I'm switching here computer, so, oh, sorry, this is the wrong screen I'm sharing.
So I will proceed with the introduction. Tim did his PhD in computer science at the Autonomous Intelligent Systems Group with Professor Wolfram Burgard at the University of Freiburg in Germany. After PhD, he moved to position of senior researcher, and he's now a junior research group leader at University of Freiburg. He's doing exciting work in machine learning for robotics, and today he's going to talk about his recent work on titled From Reactive to Human-like Semantic Reasoning in Mobile Manipulation. And
yeah, I'm really sorry, my browser is not allowing me to share the screen. Let me just reconnect with this here really quick. I'm really sorry. Everything's going wrong today. Let me just reconnect here really quick.
Of course, you know, as usual, there is always some connection problems. This is normal.
Yeah, I'll be with you in a second. Let me just reconnect on this other computer.
I will. In the meantime, we had planned some advertisement for the end of the workshop, but I will maybe start with them now so that we save some time at the end. My goal was to advertise the ELLIS PhD program. So I would like to advertise, so tell you if there are some to-be PhD students or sort of master students who are looking for PhD in machine learning driven fields in Europe. There is an ELLIS PhD program which has an application deadline in the fall, in November 2024. And the accepted students will work with 2 advisors at 2 different ELLIS locations in Europe, at 2 different countries. So there is information about the program online. I will post a link here in the chat, and I encourage prospective students to apply to this ELLIS PhD program. And it seems that we have the slides online. It seems to work well. So Tim, thank you very much for joining us, and the floor is yours. Thank you.
Yeah, yes, sorry again about all this hustle. So yeah, let me just start from the beginning. So thanks a lot for inviting me, and thanks a lot for the nice introduction. So the talk today will be again about the different reasoning levels you have in mobile manipulation. So this ranges from basically decision making on motion level or trajectory generation level up to complex decision making for long horizon tasks. So the goal of the research we have here in Freiburg, or one of the research goals here, is that we want to drive a bit forward to the field of assistive robots in human-centered environments. And there are basically 2 main research questions that we deal with. So the first one being to how can we actually learn mobile manipulation skills? So meaning in the sense of single actions, something like opening a fridge like this here, so more on a trajectory level. And then the second question is, how can we actually combine multiple of these single skills in order to solve complex tasks? So meaning then more on an abstract long horizon reasoning level. So there are several challenges we face in this field, and they're mostly dealing with that the environments we are in often are unexplored, and they might be dynamic. So we have only partial observability of the environment, and there might be some dynamics in them. Other challenges are that actually for doing manipulation, we have this large continuous combined action space of the robot base and robot arm. And what many approaches out there actually try to do is just to separate the navigation from the manipulation, but this sort of introduces some motion restrictions on what the robot can actually do, and we would like to try to avoid this. Another problem that we face is that the scenes can become quite large if you do mobile manipulation, and then you need some efficient representation of the scene and also some sort of spatial and temporal memory. But even if you have this compact representation, you still face a high dimensional observation and action space, because basically this will scale with the number of objects you have and the number of different interactions you can perform on these objects. So what we do is basically, and this is what I want to talk today, is try to modularize things a bit. And what we actually try to do is to separate this into different points. So the first thing we do is more learning on the skill side of mobile manipulation. This is the first work I'm going to talk about. And then the other 2 will be a bit more about the long horizon reasoning. Okay, so let's just dive into the first one for skill learning for mobile manipulation. So usually, I'm sorry about the messing up of the slides here, it's just because I'm using different format now. So in mobile manipulation, it's actually defining this whole body motions is highly challenging. So, but on the other hand, many tasks can actually just be defined by the end effector motion. So consider something like the robot should open this door here. It's quite easy for us to say, okay, then the end effector needs to move to the handle of the door to push it down and then push the door open. So this is quite expressive and simple to specify. But then if you want to also specify the motion that the base should take in order to make this possible, this is quite complex because it requires some knowledge about the kinematics of the robot. So it's not really clear what the base should do. And so what we came up with doing is that we train an agent that will just take over the motion of the base in a reactive manner to just allow for the desired motion of the end effector. And so this is how this works. So this builds first on an end effector planner that is basically just a system, can be an arbitrary system that just provides a motion for the end effector. So this could be learned with imitation learning or some reinforcement learning policy. And for training, actually, what we use is just a star planner that just takes randomized goals and then just plans trajectories to that goal. So the only thing it needs to do is to provide it with a velocity for the next time step. And then the thing we want to train here is the base agent, which will be responsible for providing motions of the base. This will take this velocity that the end effector should take as an input. It also takes as an input the obstacle or local occupancy map around the robot and the general state of the robot, so meaning like the kinematics of the robot. And then what it will learn to output is a velocity for the robot base, so meaning in which direction it should move, and also a velocity for moving the torso up and down, and also scaling this velocity from the end effector. All of this we can then pass to an inverse kinematic solver to solve for the remaining arm joints. And if this is possible, we can then give a positive reward, because this means that the motion that the base agent shows was actually keeping the motion kinematically feasible. If the case solver is not able to find a solution, we can then just give a negative reward and execute the motion if it's possible, and also derive rewards whether the agent collides with the environment or not. So then we have a really dense reward signal because we get this in every step the agent takes. And then with this reward signal, we can then really efficiently train this base agent for arbitrary motions. So I have here a video of how this then looks in action. So here, this is the trained agent moving the base of the robot around. So it was actually trained in simulation, but it does have a zero-shot transfer to real world because everything we train it on is just the state of the robot and this local occupancy map, which don't really have a big sim to real gap. So it transfers quite nicely. And what's also really nice that it has this emergent behavior that can actually also deviate these dynamic obstacles I'm pushing in the way of the robot. So it's actually not even included in the training. And also the motion the end effector is doing is nothing it has seen in training, because here it's now just doing some random pick and place action with some objects in the scene. So this was not actually included in the training. It's also really cool that we can use the exact same system for different robots. So on top here, you see the PR2 robot doing this. On the bottom, we have the Toyota HSR robot. I mean, they have individual agent trained for each of them, but actually the motion the end effector execute could be the same on both of these systems, because we're now shifting the complexity away from the end effector planner to the base agent of the robot. Okay, so what did we get with this now? So overall, this now allows us to really come up with easy specification of skills, because we transferred the complexity of looking out for the kinematic feasibility to the reinforcement learning agent. And the system itself is then fully reactive to dynamic obstacles. And we will see in a second, this will provide us a building block for short horizon reactive motion execution. And we will then use it as a backbone for more complex hierarchical systems. Yeah, so what is still missing? So we're now able to perform single actions or skills, but if we really want to do tasks in human-centered environments, these tasks usually consist of multiple skills, right? And additional complication might be that we don't even know the environment beforehand before performing any skill, or the objects that should be part of the skill that we want to manipulate in the skill might actually not be known where they actually are. Additional complication might be that there might be blocked pathways, so the doors of the environment might be closed, or the objects we actually want to do something with might be concealed in some receptacles like a cabinet here or some drawers. So in order to actually do something in this environment, the agent will actually need to shape the scene to solve the task, like meaning interact with the scene. And this is what we address here as an interactive multi-object search. So in this setting, the agent starts in some unexplored environment and is tasked with finding up to 6 target classes. And in this context, it now has to reason about exploration, navigation, and manipulation. And you can imagine that this largely increases the possible interaction with the environment, because the scene can be really big. And if you would try to actually just learn this in low-level action space, this is really deemed to fail. So what we try to do instead is to modularize this and build an hierarchical agent for this. So here is an overview of how this looks. So what the system we build basically takes as an input is something like a localization for our robot, then takes a semantic image and a depth image. And it uses this to create a semantic map of the environment. And from the semantic map, it can already derive what valid actions it could take. So meaning if, for instance, it knows it can interact with cabinets in this environment, it needs to find a cabinet before, so it needs to be marked on the map before it can actually choose that action. Then the semantic map and this vector of valid actions, the robot state, and the targets we're actually looking for are input to this high-level policy, which is then trained to choose one of these sub-policies that are a bit simpler. So the first policy it can choose is sort of a local exploration, which is pre-trained model that is good to uncover new regions on the map. It can also choose to do some instance navigation, meaning that it can just navigate to any instance of object it has already discovered on the map. We can also do some object interaction and manipulation. This would then build up on the pipeline I've shown you in the first part. Or it could do some global exploration, which would just mean to drive to some frontier points on the edge of the map to regions that are undiscovered yet. Okay, so what did we get with this? So now we introduced this novel interactive search task and show that this can actually be solved with an hierarchical agent. So it was quite efficient to have these high-level observations just consisting of the map and this action-based design of having these sub-policies. And we also realized that having this abstraction from this fine-grained decision is really essential if you want to have long-term, long-horizon autonomy. And the reasoning we had here was not only based on the map and the object instances. So what is still missing to perform even better is to actually really use the semantics of the scene. So ideally, the robot should use the semantic context of the scene and also some semantic background knowledge about the task in order to guide this search. So for instance, if you're looking for a coffee mug, for us as humans, it's quite clear from context that searching through a cabinet in the bathroom is not going to be really efficient. So next we thought, how can we incorporate this kind of knowledge into a system like this? And so the answer for us was by basically using human knowledge encoded in large language models. So most of you have probably seen this, that in the last year, the large language models have been demonstrated to show good capability to provide high-level reasoning for a couple different tasks, like tabletop simulations or some reasoning on fully observable environments. And so what we wanted to do is actually use this human knowledge encoded in language models to both understand and categorize the environment, and then also incorporate some background knowledge about the task in order to use this to guide the exploration. And with this, we would then have an actually semantically aware interactive object search. So the idea that we follow here is that we would like to collect and compress the semantic information that we get from the perception in a dynamic scene graph. So what do I mean by this? So basically, we divide our environment here into different rooms. So for instance, a kitchen, and then would associate all the objects we've seen in this part of the environment with this node. So having this graph structure of the scene. And then which having these semantic labels on them, we can actually ground the scene and also the language instructions for the task in a representation that's interpretable by the large language model, and then really just use large language model for reasoning. So how does that look? So similar overview or similar structure than we had before. So again, we have some RGBD and semantics as an input to this and the localization of the robot. And from this, we then build the hierarchical scene graph. So we start with building an occupancy map, then divide this occupancy map into different rooms. Then we associate the objects we have seen to this separated rooms, and then actually query a language model in order to do the room classification for us, just based on the object we've seen in this. And this then allows us to build this labeled scene graph, which contains the different rooms and the different objects. So we can then pass this as a structured knowledge representation together with this natural language description of the task to the large language model, which is then queried to decide what the robot agent should do next. So again, it will be able to choose from a set of different actions. These are quite similar than before, so it could just do a navigation to some point of the map or to some object instance on the map. The second option it has is to perform some manipulation. So for instance, opening a drawer it has discovered in the environment. And for this, we would then fall back on the mobile manipulation system I've shown in the first part. And the third option would be to do this frontier exploration, which just means to drive to some frontier at the uncovered map, so parts of the map it hasn't seen before. Also have a video of this on what this can now do. Okay, so here, I hope you can still see the screen. So what is this task with now is that the robot here gets the task that it should find something for breakfast. What it does, it looks around in the room it starts in, then based on the object it has seen, and this realizes that this is probably a living room, so not really worth exploring if it can find something for breakfast in there. So instead it chooses to open the door that it has seen. And then actually it realizes that the adjacent room is a kitchen, just based on it has seen some cereals and some coffee and a closed fridge. And then it reasons that the next action that's going to be probably helpful is go and open the closed fridge in the kitchen, because it has already seen that there were some cereals in the scene, and the cereals together with some milk that might be in the kitchen. So this is how it actually comes up with the decision of opening the fridge, would then make a good breakfast. And so it opens the fridge using this mobile manipulation pipeline from the first part, and then actually finds some milk in there, and then comes up with the reasoning that the cereals and milk can be used to make a bowl of cereal. And with this, basically, it says then that the action is done because it found enough to make a good breakfast. So this already brings me to the conclusion of the talk. So what we've seen here was that we can use a compact and expressive representation of the scene using these dynamic scene graphs that we build up while exploring the environment, and that using large language models for reasoning allows us to make use of some task context, and also to understand the environment from the perceived semantics, and then actually even do open vocabulary task solving. And I hope in the end that this will bring us a step closer to human-like reasoning and acting in robotics. So yeah. this was work done with these coworkers of mine, with Daniel, Martin, and also Abhinav. And if you're interested in any of these research projects, I have the links here. So again, sorry for making this so hard. And thanks for your attention. And if you have any questions, I'm open for them now.
Thank you very much, Tim, for a wonderful talk. I'm glad it worked out in the end.
Yeah,
Please,
me too.
for all the attendees, you can put questions in the chat or on the Slido. I will start with one question. In the last video, I've seen that there are several of these markers, like the tags on the objects. So I mean, does it mean that you're actually not using kind of a real object recognition, that you're using tags in this? And then I guess, so the language models, there are these new, class of models which also kind of understand the visual information. So it may be possible to actually do now both the visual and language reasoning. Can you comment on this, please?
Yes, of course. So, I mean, you're absolutely right. We're not doing any vision actually in this. So what we're doing here is we pre-build a map and just annotated it with the semantics and then just uncover it by using the depth sensor of the camera. So we're trying, I mean, this work was really about the reasoning given the semantics. So we're not actually trying to estimate the semantics here, but I'm assuming this could be replaced. I mean, of course, it will degrade the performance a bit, but it could be replaced by an actual semantic segmentation pipeline, but we just didn't integrate this yet because the work itself was really more about the reasoning and not the perception part of this.
Yes, I think you're right, is that, I mean, the recognition is sort of getting better and better, and especially, with these language models. So I guess, but then you would replace, say, the serial box. When you recognize the tag, you would say it's a serial box in natural language. That's how you put in the semantics?
More or less, yeah. So it would place this on the map first as a particular category, and then from the map, we would extract the label to put in the scene graph, yeah.
Okay. So, but then to communicate what you have in the language model, it would be in a natural language description, I assume.
Yes.
Yeah. Okay. Yes. There are more questions from the Slido. First one: are there known research limitations of semantic navigation in the context of semantic saturation of the environment other than the living room? I guess this is more about generalization to different environments, I guess, or how you interpret this.
Sorry, can you
Yeah, so it talks about limitations of the
I see the question. Oh, yeah.
In the context of semantic saturation. I don't quite understand semantic saturation, but I guess it seems generalization from the last sentence.
I mean, so we're doing this open vocabulary. So since this labeling of the environment is also done by the language model, it only has to deal with the labels it also comes up with, right? So not really sure how to comment this besides this. So, I mean, with this representation, we can actually build up quite large scenes, and there's nothing stopping us from also having the same room over and over again. It would just be classified based on the objects that are inside of it. What it also can do if there is some objects that are, so if it's a confusing, like a mixture of a living room and a kitchen, it would also come up with a label that represents this, so like a combined living room and kitchen. So can also do stuff like this. It's also not a problem.
I guess the language model is quite general, so as long as you put in the semantics in the language model, it should sort of be able to handle it. There's the last question. Do you think you could use the scene graph with external knowledge, like knowledge graphs, for replacing the LLM reasoning?
Could be, but I guess we lose a bit of this. I mean, depends on how much knowledge you can include in your knowledge graph, right? I mean, what the language model is really good at is providing us with this background for the task. Like if it says something like I need something for breakfast, it will know that it needs to search a kitchen. I mean, if you can include this knowledge in a knowledge graph, then would also be fine, but you need to build up this first, and where does this information come from? So the nice thing about the language model is that it can really readily do this for basically any task, and you don't need to train anything again anymore for this type of reasoning here.
Okay, so thank you very much. So thank you very much for the talk. We are out of time, so no other questions. But it was great that you could join us, and thank you very much. And I think so we are at the end of the workshop. I would like, so before to give the word to Rostislav for the final word, I would like to also thank Katerina Zorina, who was instrumental in organizing the logistic of this workshop, managing the Zoom. Katerina, if you can say hi, that would be great. Thank you very much.
Yes, hello. Thank you for organizing and making me part of this. I think it went really well. I don't have anything else to say.
Thank you very much for your help. And with this, of course, I would like to thank all the speakers and all the participants, and I will give the word to Rostislav for the final few sentences. Rostislav, please.
Thank you, Josef. I would also like to thank you, Josef, and Katerina for immense help with organizing these very, very fruitful workshop. And certainly, I'd like to thank all the participants and all the speakers for the first time. We hope that this workshop has already served a good and enlightening stimulus for younger researcher and has given a broader picture of the current state of the research in these two topics we covered today. We plan to continue this format in the future with other topics like NLP and ML for biology, for instance. So please send us your suggestions if you are interested in particular topics or even particular speaker. Also, we in ELLIS Associate Unit Lviv want to extend our collaboration within the ELLIS network. And to this end, we'll distribute the matchmaking form so that the ELLIS researchers willing to co-mentor or host Lviv master or PhD students can suggest areas or of expertise and concrete research projects. So that's probably the last announcement, and I'd like to thank again all participants and all speakers, and Josef and Katerina. Thank you very much. There were actually over 20 people here in the room. We organized a live broadcasting for the students, and so that was very, very nice atmosphere. Thank you.
Thank you very much, all the speakers, all the participants. Thank you, Rostislav. So this is the end of the workshop. Thank you.
Okay, I'm ending this call. Thank you so much. See you on the next workshops.
See you next one.
See you at the next workshop.